To begin with the first session, we have Professor Amol Dhige with us, and the topic is Supernovas, Neutrinos. What will we learn? I welcome you, sir, on behalf of the organizers. Over to you, sir.
Okay. Thank you. Can I share my screen? I think right now it seems to be
Y-
disabled.
Yeah, 1 minute, sir. I'll
Sure.
share. Yeah.
Okay, yeah, now I can share. Let me just check. Okay, can you see my screen now?
Yeah, visible, sir. Visible, sir.
Okay, okay. So let me start. Okay, so this is our first, third lecture together. In the first lecture, we saw some introduction to how a supernova explodes and how neutrinos come out and their properties. In the second lecture, we saw what happens to these neutrinos as they come out from the star and all the way to the Earth to our detector. Okay, so and what we focused on was the oscillations of these neutrinos, which means how these neutrinos go from being electron neutrino to muon neutrino or muon to electron, electron to tau, and so on and so forth. Okay. Today, we will now go to slightly more practical aspects, which is what can we learn from supernova neutrinos. Okay? And in order to understand what we can learn, of course, what happens to neutrinos, which is what we covered in lecture number 2, is going to be very, very handy. So we will use many of the results that we saw in yesterday's class, and we are going to proceed from there. Okay. So this is to remind you of all what this background is. So the background is that a star is exploding. And we saw that the star explodes via the mediation of four different fundamental forces. Initially, there is a collapse phase in which the core, which is made up of iron, becomes very dense because gravity makes it collapse, and the pressure that is applied due to what's called electron degeneracy is not enough to keep the star of a given shape. So this core collapses from about 8,000 kilometers all the way down to almost 10 kilometers. That means that the density increases really, really by a huge amount and reaches almost nuclear densities, at which time the strong nuclear forces come into play, which, as we know, are repulsive at very, very short distances. Okay? And as a result of that repulsion, this implosion converts into an explosion, okay? And the matter which is in falling now is thrown out with a very large speed. This matter cannot come out all the way because there is this whole outside star, which is yellow in this particular figure, which is still falling inside. And that prevents the shock wave from coming out completely, and sometimes it even can stall the shock wave so the supernova does not explode. However, at the same time, neutrinos which are trapped inside or behind the shock wave are trying to come out. Many of them come out, but some of them which are trapped keep on transferring the energy to a shock wave. This push that they give to the shock wave actually helps the shock wave in having enough energy to start what are called as instabilities. These instabilities, combined with all the electromagnetic forces or hydrodynamic forces, actually help in exploding the star. Okay? So that's our current understanding of how a supernova explodes. And all that we are doing is going to be based on this model. So when we try to learn something, we'll also try to learn something about this model. Because remember that all the processes that are explained here are in some sense theoretical processes. We have not seen them. We expect that these will happen. If you want to see a supernova explode, we will see a supernova explode only after the shock wave comes all the way out to the hydrogen envelope and blows it up. What happens to the shock wave inside the supernova is completely unknown, or rather unseen. I would say it's unknown because we do know a lot of physics about it, but it is unobserved. Okay? As long as we see only with light, we cannot observe it. Okay? It's very easy to stop that. So this is a background about why is it that we are excited about looking at neutrinos coming from supernova. What do we know about neutrino fluxes? Okay. We know that neutrinos come in six types, three kind of neutrinos: electron neutrino, muon neutrino, and tau neutrino, and also their antiparticle. So that is what counts for six types. Okay. Just 1 second. I'm just trying to adjust something here. Okay. Uh, the explosion of a supernova happens in three stages. The first stage is when the shock wave has just started and the shock wave breaks the neutrinosphere. The neutrinosphere is the sphere behind which neutrinos are trapped. When the shock wave breaks the neutrinosphere, what it does is that it converts all the heavy nuclei in that region into protons. And what protons do is protons combine with electrons and give you electron neutrinos. Okay? So as a result, in that very short period, when the shock wave is crossing neutrinosphere, you get a huge burst only of electron neutrinos. Okay? So if you see in this left-hand side plot, you will notice that the burst contains mainly electron neutrinos and others are almost zero. Now this happens for the first maybe a few tenths of milliseconds. Okay, so if you look at the time scale, this is just about 10, 20, 30 milliseconds. So this is the time when we see only electron neutrinos. Okay, and this is going to come in very handy later on. Afterwards comes what is called an accretion phase. An accretion phase means is that the shock wave is trying to move out, but at the same point of time, more and more outside matter is going to accrete on the shock wave, trying to stop it from going ahead. Okay. Now, by this time, along with electron neutrinos, you also get electron antineutrinos, we are shown here by nu E bar, and you also get neutrinos of all other flavors, which are here called as nu X. Nu X means nu mu, nu mu bar, nu tau, and nu tau bar. Okay, so the top figure here shows you the fluxes of nu E bar, and nu X, and as you see, they are in decreasing order. After some time, so you can forget about the explosion triggered part because this has to do with their own simulation. Okay, so this accretion phase lasts for about 1 second. Okay, this is about 0.0 seconds to zero point 0.8 seconds, so about 1 second. After about 1 second is over, then the fluxes of all flavors are almost similar. Okay, so you will see here in the third plot on top, all the three flavors are very, very similar. Okay, so in three phases, therefore, we have the neutrino flavors in different proportions. Now, in all of these three times, however, if you look at the average energies, you will notice that the lowest energy, average energy, always belongs to electron neutrino. Slightly above intermediate is for nu E bar, and slightly above that is nu X. Okay, so sometimes this hierarchy is broken, but what I said is approximately true. It is also going to be important in what we discuss that the average energies of neutrinos is different if you look at electron neutrino, electron antineutrino, and muon neutrinos. Okay. Also, the average luminosities are going to be different between these three flavors. Okay. We will come to some signatures, and I will point at that point of time that if all the fluxes were the same, then we would not be able to observe any oscillations. Okay. Because then even if uh, one flavor goes to another, you will never know because the initial fluxes were also the same. Okay. Uh, of course, I only gave you energies here as average energy, but what you get actually is spectrum. Okay. Uh, the spectrum actually happens to be approximately a thermal spectrum, like a black body spectrum or a Planck spectrum with a given temperature. So increasing energy basically means increasing temperature of these regards of neutrinos. Okay, so this gives you that background. Okay, so now we have our ingredients. Our ingredients are a star is exploding, and we are getting fluxes of these 6 types. Okay, nu e bar, nu mu, nu tau, nu mu bar, and nu tau bar. Okay, so we are going to go ahead with this information. We will now combine this information with what we learned in yesterday's class. Okay, so we have a picture of approximately what happens to neutrinos. So before the collapse actually happens, the neutrinos are deep inside a supernova core. They are trapped. Okay? They cannot come out. However, when the supernova explodes, the neutrinos of various flavors are emitted, like we saw on the last slide. Now, what happens to them? While they are still inside this core, with a radius of even less than 10 kilometers from the center of the star, they can undergo what are called as fast collective oscillations, okay, which, as we saw yesterday, are nonlinear oscillations, and they happen because at such large densities, the neutrinos interact with themselves, and that interaction is quite strong. Okay. So this is a very major part, and what it does, it allows neutrinos to oscillate even when they are deep inside the core. And we also notice that as a result, it is possible that the push applied by neutrinos on the shock wave can actually be quite strong. Okay, it can be different at least. Now, these neutrinos come out of the core, travel through envelope, and we saw that when they are about a few thousand kilometers from the center, they undergo two resonances called H and L resonances. And during the resonances, they can undergo some flavor conversions. Okay? Uh, in the case of smooth density profiles, we will get some nice value of probability of survivals called P and P bar. We saw that yesterday, and we also saw that that value can change if a shock wave is passing. Okay? So we will look at the shock wave in detail today. After passing through this matter, neutrinos exit the star. When they exit the star, they exit the star as matter as mass eigenstates or energy eigenstates, and the standard rule of quantum mechanics that energy eigenstates never convert to each other. So therefore, there are no neutrino oscillations all the way from the star to the Earth. Okay, so this part is completely oscillation free. Now, if a detector happens to be where it can see the supernova directly somewhere in the sky, then of course that's it. But suppose our detector is somewhere else on the Earth, which would mean that Earth will hide the supernova. Okay, so which means, let's say if I'm, let's say right now I'm in Mumbai, you guys are, no, I don't know exactly where all the people are sitting here, but for you, this supernova is going to be below the ground. Okay, because it will be no, the supernova is going to be on the other side of the Earth, and therefore, if you have a detector near you, to reach that detector, the neutrinos have to travel through the Earth. Okay? It's not a problem for them because neutrinos can always travel through the Earth without doing anything. But once they enter the Earth, they are no longer energy eigenstates, and therefore there are further flavor oscillations. And we saw yesterday that these flavor oscillations actually can be seen perhaps at a detector. We will see more about that. Okay. So this lecture is about what can we actually learn or what can be observed given whatever we studied yesterday. So we should focus on two main problems that we want to address. Problem number one is what can we learn about neutrino mixing. Uh, a major thing in neutrino mixing that we saw yesterday was that the neutrino mass pattern can be of two types. There can be, the pattern can be like I have here on the left, which is called as normal ordering, or sometimes it's called normal hierarchy. The pattern on the right is called as inverted ordering or called as inverted hierarchy. Now we do not know which of these pattern is the correct pattern. But again, as we saw yesterday, the neutrino flavor changes depend crucially on what kind of neutrino pattern is actually there in nature. Okay? Therefore, we expect that when we see some neutrinos actually uh, at our detector, one of the things we may be able to find is what is this mixing pattern, okay, normal or inverted. Second thing we would like to learn is about supernova interior. Okay, so as we have seen many times, we don't really know the astrophysics that happen inside a supernova. It depends, firstly, of course, on the medium, because as Datar talked about in this last few lectures, there's a lot of astrophysics that happens inside a supernova, neutrino nucleus interactions. Uh, there are, of course, nuclei are trying to fuse all the time or decay all the time, converting to their isotopes and so on and so forth. That all thing is not known to us. Uh, for the bouncing of shock wave, you need what is known as called as equation of state of the nuclear matter, and we don't know that because we don't know exactly what kind of nuclear matter is there. So all this information is unknown, and as a result, we don't really know exactly what are the neutrino fluxes coming out. So although I showed you some fluxes in a neutronization burst or an accretion region with a lot of confidence, uh, these fluxes are not really known to much accuracy than, let's say, 20, 30, 50%. We don't know them to 5% accuracy. As a result, all the result that we would get could be tentative. So what is our job? Our job is to find out those signals at the detector which are robust. Okay, it means that these signals should not depend on the exact knowledge of initial neutrino fluxes, and they should not depend on the exact knowledge of what's happening inside the star. On the other hand, what we'll try doing is we'll try to see if we can figure out what's happening inside the star by looking at neutrinos. So in that sense, the focus is going to be learning about these two things, about neutrino mixing itself and about what happens inside a supernova, how does it explode, how does the shock wave propagate, and so on and so forth. Okay. Uh, are there any questions at this point of time? Okay. So
No,
I
sir.
good. So I don't see any. Okay.
Yes, sir.
So let's try to learn something from history first. Okay. And the history of the supernova is actually not very long. We have only seen neutrinos coming from one supernova so far, and that happened in 1987A. Okay. So the question now is, what did we learn from 87A? So let me take you back to what we observed in 87A. Okay. So we saw these two figures, these two plots, and let's look at them in detail. Okay. So there were three detectors which observed this burst: Kamiokande, IMB, and Baksa. And each of the points that you see is one neutrino. Okay. So no Kamiokande, therefore you can say Kamiokande observed, I don't know what this number is, about 15, 3, 4, 5, 6, 7, 8, 11 neutrinos. IMB observed some 8 or so, Baksanas observed 5. So information is quite meager actually. Okay. You can see the time in which they came, and they came in maybe about 10 seconds. Maybe you can say 12 seconds, 15 seconds. It's almost like a statistically fluctuating signal. Okay, it's the signal overall is very small. On the other hand, we observed a lot of light from the supernova. Okay, so you can look at the light curve, and maybe it's a good idea to understand how to read light curves. This x-axis years after explosion. Okay, because supernova is of course visible for many years. Initially, it was visible by telescopes on the ground. That's why it's called as ground-based observations. And later on, it became very faint, but Hubble Space Telescope could see that. And if you remember, there was an image that I showed you. So what does this show? This shows what is called as apparent magnitude. Okay? Magnitude of a star is a logarithmic scale. magnitude of sun is supposed to be is 1, and if a star is 1/10 the brightness of sun, the magnitude is going to be 1. If it's 1 upon 100, magnitude is 2. If 1 by 1000, magnitude is 3. Okay. So if you look at this, you will see that the magnitude actually has gone up to almost 3, I guess, or 2 are coming back. And tells you that the star therefore was quite was quite bright. Okay. I'm sorry, the one is not sun's magnitude, one is the magnitude of a standard the standard magnitude of the one of the brightest stars that we can see. Now this you see in the red band, which means in the wavelength corresponding to red light, and in the blue band, just so that you know the dependence on frequency. On the right hand side here, you will see a scale called luminosity, and you will notice that as luminosity increases, magnitude decreases, right? It goes as 20, 15, 10, as luminosity increases from minus 10 power minus 10, sorry, 10 power 2, 10 power 4, and so on. So a curve going down like this simply means that uh, the light is decreasing, the intensity of light is decreasing. However, this light, as you see here, can be seen for almost, this is up to 10 years, but of course we can still see it from Hubble telescope, so almost 30, 35 years. Neutrinos, on the other hand, if you see on the left hand side, came in only 10 seconds. So this is a very big difference between the light from a supernova and neutrinos from a supernova, that you only have 10 seconds to observe neutrinos coming from a supernova. After that, the intensity will become so low that you will not observe any neutrinos. Okay? So the time given to you is only 10 seconds. Okay? On the other hand, as we saw yesterday, number of neutrinos coming, at least those that start from the star, are of the order of 10 to the power 58. And that's why at the current detectors, we will be able to see many of them. I will come to some of these numbers in a while. Okay? So these neutrinos which came from 87A are only about, let's say, 25 in number, okay, maybe 30. So really they can't tell you much. Okay? So what did they tell us? The first thing that they did is they confirmed our understanding of supernova cooling mechanism. Okay? So because we of course know that supernova cools because we can observe its temperature decreasing. Okay. However, understanding of nuclear reactions tells us that when supernova cools, 99% of its energy should come out in neutrinos. Now, for this, there was no other observational evidence before 1987. Okay. So, 1987, when we actually saw neutrinos, it told us that indeed, yes, these 25 neutrinos that came corresponds to almost the energy of an exploding star. So, this 25 neutrinos implies that the number of neutrinos which actually started would have been 10 to the power 58. We could do that calculation, and therefore it showed us that all the energy actually came in neutrinos. Beyond this, 20 events don't tell you much. Okay, so we could not say much about neutrino mixing, for example. It was very hard to say anything. However, we obtained some constraints on supernova parameters. Okay, so, for example, this would tell us how big a supernova was, because energy that is emitted in neutrinos cannot be bigger than the energy of the star, clearly. So that told us that the energy of the star must be larger than a certain value. Another interesting thing that looking at this supernova burst told us is that uh, apart from neutrinos, no other extra new particles have come out, at least not significantly. So you see, suppose along with neutrinos, some other unknown particles also came out, it will mean that the star will cool much quicker. Okay? Instead of cooling down in 10 seconds, it would cool down in 5 seconds or 2 seconds. Okay? The calculation that shows that neutrino cooling cools down the star in about 10 seconds is very, very robust. The fact that we actually observed neutrinos coming till 10 seconds or till 10 seconds, and not the neutrino flux did not stop at 5 seconds, tells us that nothing else is coming out apart from neutrinos. Okay, not for a large extent. And what that does is that puts very strong constraints on new physics models. Okay? So theorists like me are very creative and also very let's say, even without having evidence, we like to propose new particles just to see what they will do. So there are many kinds of new physics models which are proposed by theorists about the neutrinos decay, whether inside supernova there are particles called axions that get produced and they come out, or particles called as majorons which may come out. Some people said, okay, maybe they're extra dimensions and we could see them inside a supernova, and that might do something. However, all these processes would make the star cool down much faster. Okay, the fact that we saw the event for about neutrinos for about 10 seconds actually told us that at least these scenarios are not very strong. Yes. So I agree with the comment made by Professor Murthy. Theories propose, experimentalists dispose, right? So experimentalists, by simple observation of 25 neutrinos in 10 seconds, was enough for many of these models to go in the dustbin. Okay. We of course know we go scratch the dustbin and try to make something more out of them, but at least we knew that the supernova explosion in the supernova explosion, these kinds of fancy scenarios do not play much part. Okay, so that was something that came out from 1987. Uh, any questions at this point? Okay. So of course this was long ago. This was in 1987. Now we are 34 years past that. Okay, and we now have bigger detectors, better detectors. Okay, so our question now should be, what can we observe at the current detectors or upcoming detectors? Okay, so I will of course give only a limited perspective from a theory side. Whatever I know about detectors is quite limited, but however, Professor Kate Schulberg, who will give the concluding lecture, will talk about this in more detail. Okay, so let me give you a short summary of what is it that we should be looking at. Okay, so these are the sort of detectors that currently exist with us, which can see a lot of events from a supernova. The number of events from a supernova will of course depend on how far the supernova is. So what is done here is you assume that there is a supernova at a distance of about 10 kiloparsecs from us. Now why 10 kiloparsec? We are at a distance of about 8 kiloparsecs from the center of our galaxy. Okay? And therefore we know that no, around galactic center, if you look at that region, there will be more number of stars. So it's possible that more number of supernovae are in that. So this is just taken as an assumption. After that, of course, if you know that the supernova explodes at 1 kiloparsec, it will mean that the flux will be 100 times, right? Because it's 1 upon r square. Okay, so this is sort of a standard distance at which you predict number of events. So what are these detectors? Okay. So detectors come in different categories. The one that we are familiar with, which I mentioned in last talk also, is Super Kamiokande, which is a detector made up of water Cherenkov. And if a supernova happens tomorrow in the sky, for example, Super Kamiokande, which is in Japan, will be able to observe about 10,000 events. Okay, so that's 10 to the power 4 events. Okay, that's the biggest one. Now, we also have a detector at the South Pole called as Ice Cube, which is called Ice Cherenkov, and it was mentioned in the public lecture on the first day by Professor Kate Schulberg. Now, this detector consists of many photomultiplier tubes buried deep inside ice, and you could actually see about 10 to the power 6 events there. However, only caveat is that inside Super Kamiokande, you can see a neutrino producing an electron which leaves Cherenkov light, so you can actually look at it event by event. In Ice Cube, because the energy of neutrinos from supernova is very low, it is not possible to see each neutrino separately. But what you actually see is you look at the total number of uh, light that the photomultiplier tubes see, and when the supernova explodes, those number of photons is going to go quite high, and it will go high by almost about a million. And that is the reason that ice cube, this number say 10 to the power 6, but just a caveat is ice cube cannot measure individual neutrinos and its energies. However, it can measure the total luminosity of neutrinos that is coming. Okay. Uh, then there are other detectors which are slightly smaller, and if you see number of events that are possible there are a few hundreds. Okay. So Diabe is a, I think, a scintillation detector. So is Camland. Diabe was used to determine the reactor mixing angle, Camland for the solar mixing angle, and then there are other detectors called Buxan, LVD, Borexino, SNO plus, which are all scintillation type. The detector called as Halo, which is made up of lead, and that can only see a few tens of units. However, we are of course waiting for bigger detectors. Soon, instead of in addition to Super Kamiokande in Japan, there will be a detector called Hyper Kamiokande, which will be hundreds of kilotons, and we'll see almost of the order of few lakh events. And in the US, there's a detector called as Dune, uh, on which Professor Scholberg also is working, and that is made up of liquid argon. It will see of the order of a few times 10 to the power 4. The only seeing neutrinos is perhaps not enough. We have to see what in the neutrinos can we see. So for that, we have to look at nuclear reactions. Okay, because we observe everything from nuclear reactions. Even when you observe neutrinos at the Earth, we observe them by nuclear reactions. Okay? So let's see nuclear reactions that take place in typical detectors. Okay, again, this is not entire all details, but just some examples. In a detector like water Cherenkov detector, like Super Kamiokande, when electron antineutrinos come, they interact with proton. Okay? Now, proton exists in water because, of course, water has hydrogen and oxygen. Hydrogen has protons. This interaction gives you neutrons and a positron. Okay, and you can are able to observe this positron through Cherenkov light, and at Super Kamiokande, you can see of the order of 10,000 events of this type. If any other kind of neutrinos come, okay, they can still interact with the electron, and they scatter the electrons. Electron starts moving with a very fast speed, and there'll be a few hundred events of this type. Okay. Uh, Electron neutrinos also can interact with oxygen. Okay, it gives you X just means something that I cannot see the detector, but I will see an electron. Okay, not a positron. Uh, uh, and there will be about 500 or so events of this kind. So this is what happens in the water Cherenkov detector. Okay. And this positron is the one that gives us information about the energy of the incoming antineutrino. Uh, yeah, so that's what happens in a uh, water Cherenkov detector. Okay. In scintillation detectors, of course, this reaction is always major. Electron antineutrinos interact with proton to give you neutron and positron. In addition, because scintillators mainly has carbon, the neutrino can interact with carbon and go to an excited carbon state, which when de-excites can give you a photon of a fixed energy, and this could help in identifying this particular reaction. These neutrinos can also interact with proton and scatter the proton. And if you can measure energies very accurately, maybe you will have access to this particular reaction also. So note that in both of these types, the main uh, reaction that you can observe is the top one. It is also sometimes called as inverse beta decay. It is like beta decay of neutron, but just inverse. And this gives out a positron. This interaction happens only with electron antineutrino, and that's very important because this would mean that these detectors would not allow us to look at electron neutrinos. On the other hand, if you have a liquid argon detector, you can have this interaction where the electron neutrino interacts with argon to make it excited state of potassium 40 and gives an electron, and this will help you also look at the electron neutrinos. So depending on what detector you have, your strength is to determine different things. What is it that we'll be able to see now? Let's say look at electron neutrinos first, and as we just saw, the liquid argon detector like Dune, you will be able to look at electron neutrinos and you will be able to reconstruct the spectrum of their fluxes, because the energy of this electron that comes out will be sort of similar to the energy of neutrino that hit you. In the water Cherenkov, similarly, you can reconstruct energy of electron antineutrino, the spectrum of antineutrino. The detector like ice Cherenkov, like ice cube, you can see the total luminosity of this detector, of electron antineutrino. Remember, not about electron neutrino. In scintillar detectors, it is possible, though it's very difficult, to find a total flux of this, simply because finding energy of individual ones is quite difficult, but it's possible to get some handle on the total flux of this because of the reaction that we saw earlier, mainly the reaction that has scattering of neutrinos on proton, okay, because this is the neutral current interaction. In lead detector, you can see events which are called as a single neutron and double neutron events. So it again tells you something about electron neutrinos, but not much, because the number of events here is going to be very, very small. If you remember this past plot, you will see that while supercabochondriasis is 10 to the power 4, halo will see only a few tens. Okay, so that information is not much. It's a complementary information, but not great information. Okay. Once we observe this at many detectors, we can infer certain quantities, which are the quantities that we are going to deal with. So what can we infer? We can infer, let's say, average energies of neutrinos, not of nu e, nu x, not of nu tau maybe, but maybe of nu e and nu e bar. We can infer spectral shape, again for nu e and nu e bar. If we look at different times, we can see time modulation of flux, especially at a detector like ice cube. We can actually see as a function of time how our neutrino fluxes change. Okay? We can compare two detectors. So I can say, for example, that I will compare what happens at ice cube with what happens at supercabochondriasis as a function of time. Okay, we expect that without anything else, what ice cube observes and what supercabochondriasis observes should be exactly the same, except in a very, very special scenario where the neutrinos come directly to ice cube but have to pass through Earth to reach supercabochondriasis. In that case, ice cube will not observe Earth matter effects, but supercabochondriasis will observe Earth matter effects. Okay, so that is something that we may be able to observe. In a detector that is like which can determine the spectrum of neutrinos, we can also perhaps see oscillatory modulations. Right? Yesterday we saw that it's possible that with Earth matter effects, you can your spectrum can actually go up and down. Okay, so this is going to be our let's say information or the bag of observable things, from which we are now going to learn things about what happens in the next galactic supernova. Okay. So I will take a small halt here, perhaps look at some questions that have come up. Perhaps there are some comments. Okay. So the question is, in the standard scenario of supernova explosions, what is the area where our understanding is least and needs improvement? Okay. So as far as neutrinos are concerned, there are two regions. One is, of course, equation of state, because we don't know how things explode. And second thing is these nonlinear oscillations, about which we know nothing. Equation of state is deeply connected with shockwave propagation and how much neutrinos push it from behind. And as I explained, as mentioned a few times in the last 2 days, how much push can a neutrinos give depends on how much have they converted their flavor. So both of these issues of what happens in astrophysics and what happens in oscillation physics are deeply connected and intertwined. Okay, one cannot be solved without the other. Okay. There's another comment, which is even ICAL, which is the detector at INO, can give some information using neutron detection, like lead detectors, but using ion target. Yeah. So in this is true, and therefore even ICAL is an interesting detector for next galactic supernova. Okay. Uh, I do not see any other questions. Okay. So this is what we have. Let me take you to the last slide once more. Okay, so this is all we are going to observe. Okay, spectra of nu e and nu e bar, uh, total luminosity of nu e bar, and not so much information on other ones. Okay, it's there, but really not to that extent. Let's see what we can do with this. Okay. Firstly, thing to remember is, of course, that if we have a supernova in our galaxy, which is, let's say, about 10 kiloparsecs, we are going to see number of events which is of the order of 10,000 even right now, or in future even of the order of a few lakhs. Okay, and if you see a few lakhs of events, then of course you can very confidently reconstruct your spectrum. Okay. So let us say different physics issues which we can learn when we observe this. Okay. The first thing, which has been mentioned quite a few times in this week, is that the neutrinos from a supernova actually arrive at the Earth about 6 to 24 times before the light. Now, why does this happen? Clearly not because neutrinos travel faster than light, they do not, but it happens simply because they start earlier. Okay? As soon as collapse happens, neutrinos start. On the other hand, for light to start, the shock wave has to actually come out and has to explode the envelope. Okay, and this process of the shock wave coming and breaking up the envelope can take anywhere between 6 to 24 hours depending on the star. Okay, but what this tells us is that if we find neutrinos coming here, let's say today at 6 o'clock, it means that we know that a supernova will explode, can be seen in light in the sky sometime in the next 6 to 24 hours. Okay? Uh, you don't want to miss that because supernova in our galaxy. So, of course, you would want to inform everybody. And as was mentioned in the public lecture on the first day, there is a network called as S News Network, Supernova Early Warning System, which actually gives you a sort of warning saying that supernova is perhaps about to occur in our galaxy in the next day or so. So those who are interested, please turn your telescopes to particular region in the sky. Which region I will come to. Okay, so that is of course our aim of to find out where the supernova going to appear in the sky. It is not always sure that you will see a supernova in that those 24 hours. The reason for that is it is possible that a shock wave fails. The shock wave fails, and therefore the envelope is not blown. And then, since the envelope is not blown, you cannot see the star explode. Okay, so the explosion has somehow frizzled out. Now, once that happens, it means that. So one second, there is some problem here, perhaps. Okay, I think. Okay. So this means that there was a supernova which imploded but could not explode. And remember that if we did not have neutrinos, we won't even know of this. So we have no idea if in our galaxy some supernova would have exploded in the last many years, but if it happened before neutrino detectors tried to look for them, we will never know them. Okay? So we actually do not know how many supernova exploded in our galaxy. How many supernova collapsed in our galaxy before, let's say, before 20th century. Okay? Because before that we did not have neutrino detectors. Okay. Now, therefore, we can sometimes we will be able to look at supernova implosion and neutrinos, and either we see supernova in the next 1 day, and that's of course very great, or we will not see a supernova on the next day, and it will tell us that there was a supernova implosion but a failed explosion, so supernova did not explode. That's also something that okay. So we'll be able to identify those core collapses which did not result in exploding star, and note that before this we would not have been able to do it. So that part is quite important. Okay, it's of course not just enough to tell people that tomorrow at some point of time a supernova exploded in the sky. It's useful information but not enough. So what one would like to tell people is where the supernova is going to be in the sky. Now our question is, how do we know where the supernova is exploding in the sky? And our answer is, we will know it if we look at this interaction, which is neutrino hitting electron gives you electron scattering. So what will happen is, of course, because neutrino is very energetic, it will hit the electron, and when I hit the electron will start moving forwards. And then I can trace it backwards and see, okay, so maybe it's coming from that region. It won't be exactly the same line, because even when two balls hit each other, the ball can deviate a tiny bit, but we can have this to some extent. Okay? And as we saw, we will have about 200, 300 events in Super Kamiokande of this type. The problem is not these events. The problem is that along with these, there are going to be lots of events of the inverse beta decay type, which I earlier told you is the major signal for a supernova. The problem is that in these events, these positrons do not obey the same direction as the incoming neutrino. They can go in any direction that you want. This is therefore called as background, which is almost isotropic. And number of events of this type are of the order of 10,000. So you imagine that there are 10,000 events which are almost isotropic, in all directions. And on top of these 10,000 events, there are some 200 odd events of this forward peak type, which tells you where the star was. Okay. So background is about 30 to 50 times higher than the signal. Okay. So it's essentially like this. If you think of this as the detector, uh, the signal is coming, this blue crosses are those that come from our signal, which is the forward scattering interaction, whereas this whole green thing is the background. And the question is how to separate this. If you cannot separate this, still it is not impossible to find. I mean, by eye also you can figure out that the supernova must have come out from the other side of the Earth. Okay, so with that you can still determine supernova to within about 5 degrees. Okay? So not great, but 5 degrees is not small either, right? You can actually tell you, okay, in that region of the sky of 5 degrees, a supernova will happen in the next 24 hours. Well, not a bad information, actually quite good. However, of course, experimentalists are quite clever, and they have come up with this idea where you add salt of gadolinium to this water. What this salt does is that it absorbs this neutron and gives out a particular signal consisting of typical photons. Okay, and as a result, you can see when these reactions happen, because in these reactions, gadolinium will also absorb the neutron and give out a photon. Then you remove those events. So once you remove all these green events, you'll be left only with blue events, and then you can imagine that in that case you can find direction pretty quite nice. Okay, so in fact now very soon Super Cavalcante will have gadolinium. I don't know if it already has. I think they were planning to fill it up with gadolinium now, uh, or at least in the next few years. And then we'll be able to get this pointing to a much greater accuracy. Okay. So this is what you can do about pointing. Okay. So any questions about this pointing idea? Okay, there's a question here about something I talked about earlier. What is the difference between single and double neutron events? Yeah. So, see, this is a reaction of neutrinos happening on lead. Okay. And depending on energy of neutrino, the lead nucleus can go to an excited state. Okay. And this interaction for low neutrino energies actually releases one neutron, and if its energy is high, it can release two neutrons. Okay, that's as far as my knowledge goes. I do not know anything deeper than this. If there are anyone in the audience who knows, they can of course mention this. Yeah, so I think Professor Datar has already answered the question. Neutrino can elastically excite a lead nucleus, and depending on the energy, you can get one or two neutrons. Thanks. Okay. So pointing was one way to learn something about supernova. Remember, if you are a person or a institute which runs an optical telescope, it's a very great information for you to know where to look at to find a supernova. Okay, because otherwise, if you are going to say to wait till somebody tells you, oh, supernova has happened there, then of course turning your telescope there may maybe take you at least a few hours and you will miss some interesting initial parts. Okay, now this will mean that you can see explosion right from the minute go. You will know, no, that is the star that around that region that is going to explode, and yeah, you will be able to focus on the question. Neutrinos reach before only because it leaves neutrinos first. Yeah, that's the correct statement. Yes. Neutrinos travel with almost the speed of light, slightly less than that, not more, but they start about a day before, and therefore they arrive a day before. Okay, what else can we study? You remember that the first phase of neutrino emission was very special. It was called as neutronization burst, in which only electron neutrinos came. Okay, now these electron neutrinos, when they come, they of course have to they pass through the core, okay, where they can undergo collective effects. Turns out that you cannot have collective effects if there are only electron neutrinos, okay, because collective effects require that along with electron neutrinos you also have electron antineutrinos because they have to convert in pairs. So therefore collective effects have no impact on neutronization burst. However, the resonance H that we often referred to yesterday has a large impact. So what is the impact? I will give you the final result of this. Okay. If the ordering is normal, then at H resonance, only 0.025 of electron neutrinos are left. Everything else get converted, which means that only 2.5% of electron neutrinos are observed as electron neutrinos. Everything else is not observed. On the other hand, if the hierarchy is inverted, if ordering is inverted, 30% of electron neutrinos remain as electron neutrinos and remaining ones go up. So what do? We let's say go at a liquid argon detector, okay, like Dune, and we try to see what spectrum we will see. So what you see here, x-axis is time. Okay, this is about a few milliseconds. This window of neutralization. If there were no oscillations, the flux will be like this, which is the blue line that you see here. But of course, we never see this because we know oscillations exist. What do we not know? We don't know the ordering. If the ordering is normal, then this flux, out of this flux, only 2.5% neutrinos stay. So you see what is seen here as the red line. So basically, you will see almost no neutrinos here. On the other hand, if the ordering is inverted, you will see about 30% of them. So therefore, if you observe the neutronization burst, and if you observe only 2% of neutrinos, you know that the ordering is normal. If you observe 30% of them, the ordering is inverted. So what this means that the supernova neutrinos have done is within about 50 milliseconds, this interval, they have solved one of the major unknown problems that we have, which is to decide whether the ordering is normal or inverted. Okay, that's quite a big thing. Okay? However, to do that, we will need a liquid argon detector like Dune, we need it to find out this burst. So time resolution should be very quick. It should be within this few milliseconds, which is of course very easy for you. Okay. And as I said, it's not affected by collective effects. So this is quite fun. Okay. So these are going to be the first neutrinos which will arrive, and they actually do two things for you simultaneously. They tell you that a supernova is going to happen tomorrow, and they also tell you that uh, the hierarchy is either normal or inverted. Okay, so let me just pause here for a moment to see if there are any questions. Okay, okay. So we have learned what we have understood what we'll get from neutronization burst. Now let's go slightly ahead. Now we look at shock propagation, okay, which also has been mentioned in chat, is one of the sort of most unknown things inside a supernova about how a shock propagates. So let's see how a shock propagation will affect neutrons. Okay. So let's look at this figure. So let me explain what this figure is. This R shows you radius or distance from the center of the star in centimeters. Y-axis shows you density. Okay. Now, before a supernova explodes, the density profile looks like this black curve. You see, it is reasonably smooth. Okay, rho h is the band between 10 to the power 3 to 10 to the power 4 grams per cc. So when you are in this region, neutrinos undergo H resonance. When you are in the region of this density, which is rho L, neutrinos undergo L resonance. Okay. So if you look at this curve of 0.1 seconds, which is immediately after core bounce, you see that in both L region and L region here, H region here, profile is very smooth. Okay. If the profile is very smooth, we know the values of P and P bar. Okay. Now, at 1 second, the shock wave has been formed, and therefore the shape of the density profile becomes like this red dashes. Okay. Still, at 1 second, nothing is happening here. This profile here is smooth. Okay, in the H and L regions. At 2 seconds, the shock wave has come like this. Okay, the density profile is like this, and that means that this tail of this green curve you see has now entered H region. Okay, that means that some neutrinos will be affected now. The survival probability will change. If you go to 5 seconds, you go to this blue curve. Okay, and therefore you see that neutrinos which are coming out now are going to go through many sharp density changes. Okay, here and here. These two are the main sharp regions, but even in between there could be sharp turbulences. Okay. And if you really go much beyond, maybe at 15 seconds, you will also see sharp changes happening in the L resonance region. Okay. So especially around 2 to 5 seconds, H resonance is the region at which the neutrinos may undergo what are called as non-adiabatic flavor transformations because of shock. So when shock wave passes through resonance region, which is so between 2 to 5 seconds, matter density changes very sharply, and therefore, just for that tiny amount of time between 2 to 5 seconds, the values of P and P bar will change. Okay. So if you look at the neutrino spectra, you will observe sharp changes in the probability, and these will depend on time. So what will happen is between 2 and 5 seconds, you see something is happening. Okay. So let's not go into detail of how things are worked out. I will show you what is it that we can observe. So what we can observe is this. Okay. So look at the top curve. This curve actually shows the probability of survival. It's almost like probability P. The red curve here shows you survival probability at 2 seconds. Okay. Uh, the blue one shows 2.5 seconds. Okay, so as time progresses from 2 to 2.5 seconds, the survival probability now changes. So what I am showing here, x-axis is energy. Unfortunately, that is not shown well. So this is a function of energy. So it shows you that at 2 seconds, low energy neutrinos are affected. They survive more. At 2.5 seconds, that peak shifts to higher energy neutrinos. Okay. The red curve on the lower plot is what happens at 3 seconds. So you see that that curve has shifted to even higher energies. At 3.5, it shifts even higher energies. So what this means is if I look at the value of probability of P that we saw earlier, as time progresses, okay, that peak in that value shifts to higher and higher energies. What does this mean? It's almost like we are watching the shock wave propagate. If I see that at time 3 seconds, my shock wave corresponds to this energy, from this energy I can find out what is the density at which the shock wave currently exists. Okay. So in principle, therefore, I know I can find out from this red curve where was the shock wave at 2 seconds. This blue curve tells me where was the shock wave at 2.5 seconds. This lower red curve tells me where was the shock wave at 3 seconds. And this curve tells me where was the shock wave at 3.5 seconds. So between 2 to 5 seconds, I can actually track where the shock wave was. Now this is really, really something grand because simply by observing light from a supernova, you will never be able to say this. Because at this point of time, light is not coming from supernova. So you do not even know that there is something happening inside the star. Okay. And that is what means that in principle, we are able to track the shock wave inside a supernova. Okay. It's not ideal. It doesn't tell you exactly where it was everywhere or doesn't tell you. It tells you only what is happening along our line of sight. But still, something is better than nothing, and therefore it will be great if we'll be able to observe this shock wave propagation. This shock wave propagation does something more. Okay. If the ordering is normal or NH, normal hierarchy, then you can see the shock effects in electron neutrinos. And if the hierarchy is inverted, ordering is inverted, you see them in electron antineutrinos. So based on whether you saw these effects in neutrino or antineutrino, you will be able to say whether ordering is normal or inverted. Okay. So this in some sense will confirm your understanding that we already had got by using the neutronization burst. So both neutronization burst and shock wave will be able to tell you what kind of ordering we have. Of course, I must say that I gave you a much more rosy picture and optimistic scenario that will happen. However, there are certain caveats in this, which I will just mention. It's possible that you will see no shock effect, okay, and that of course will tell you doesn't tell you much. And it is possible that you do not see shock effects because the primary spectra, initial spectra, are very close together. As we saw, if two spectra are very close together, even if they oscillate, we will not be able to tell. Okay, so that will be quite bad. uh, Shock waves are not as simple as what I described in this. It's quite possible that even behind the shock wave, there's a lot of turbulence, and turbulence can actually make your effects much less strong. Okay, so the reason I gave you this sort of optimistic scenario is to learn about the physics that's happening behind this. And indeed, if we happen to be lucky and neutrino spectra are not too close and turbulence is not too much, we will be able to figure these things out and look at the shock wave. Okay, and that's really, really going to be something. Okay, any questions about this part about shock wave?
No, sir.
Okay, let's go to the next effect, which we did discuss yesterday, which was the earth matter effects. Okay, so remember that we saw if neutrinos have to travel through the earth to reach the detector, it is possible that the final spectra will have these kinds of oscillations in them as a function of energy. This Y is actually 1 over energy. Okay, so this is that impact. The question is, how do we detect this? Okay. So one simple thing is, of course, whenever there are periodic functions, you should look at their Fourier transforms. Okay, and if there is a function with a good periodicity, your Fourier spectrum gives you a nice peak. Okay. So indeed, that is what people saw whether this could be done, and For example, if there is a supernova which happens very close, let's say at 1 kiloparsec from us, then not so much in the water Cherenkov, which is the top figure, or in scintillator, which is the middle figure, but in liquid argon TPC detector, these authors have shown that for a really nearby supernova, one may be able to see such a peak in the Fourier transform of this particular for these oscillation frequencies. Okay. Even if this is not true, the second thing you can do is always look at luminosities at two different detectors. Right? This we saw earlier, right? So we saw that we could look at luminosity at ice cube and luminosity at super Kamiokande, and no, maybe those two luminosities will be different, and the difference between them will be because of Earth pattern effects. Okay, so this also is possible, and okay. There are certain exotic things that happen inside a star, and we really don't know whether they actually happen or not, but we can find out about them by looking at these neutrinos. Okay, one such scenario is what is called as a QCD phase transition. Okay. What does this mean? We know that let's say protons consist of two uptime quarks and one downtime quark, or a neutron consists of one uptype quark and two downtime quarks. Okay. However, at very large densities and pressures, neutrons and protons don't remain as separate entities. However, these quarks mix amongst themselves and form what is called as a quark-gluon plasma. Okay, it's something a new state of matter. At extreme environments like the supernova, it is possible that this actually happens. We of course, I would say we know that this kind of a phase transition happened long ago when our universe evolved. Initially, there was a quark-gluon plasma, and after that, protons and neutrons came into being. Okay. So this is something that can happen inside a supernova when densities become very large. So if that happens, the core will actually become compact very fast, and it turns out that at detectors like ice cube, you will get a very sharp signal uh, that you see here. Okay, so the signal that you see, so the green stuff is the noise level in ice cube or the background, and the blue thing that you see is the signal because there is a supernova explosion and neutrinos are coming out. But if a core compactifies, then in addition to having this smooth blue line, you will have very sharp peak here at here it is about 0.26 seconds. You will see a very sharp rise in the number of photons in the ice cube, which is because number of neutrinos that have come. And they tell you that it's quite possible that there is a quark-gluon plasma is being produced in the center of the star. Okay. The same thing can be seen in a detector like water Cherenkov one, like Super Kamiokande, which looks at due bar. And again, this is the number of events in Super Kamiokande. And at the same time, you will see again very sharp peak at exactly the same time. And this will confirm that actually QCD phase transition took place inside the star. Okay, and again, no, this is a process that we have never seen in nature. None of us were around when before the first minute after Big Bang there was quark-gluon plasma. We of course produce quark-gluon plasma inside Large Hadron Collider when we collide different ions together, but this will be another natural process that we will be able to observe. Okay, so indeed we can observe this quark-gluon plasma formation at isotope superconductor. I don't have a slide on this, but indeed it is also true that suppose supernova doesn't explode and a black hole is formed instead, we also can get signals of black hole formation by looking at these neutrinos. Okay. Another thing we can get information on is about explosion of star through the instabilities that I mentioned sometime back, the hydrodynamic instabilities. They are normally called as SASI instabilities or standing accretion shock instabilities. and they basically means that there are very big fluctuations in the density at a very large scale in the density inside the star. Okay? And these fluctuations can be seen in a detector like ice cube, which can see lots of events as a function of time. So you see, for example, this Dewey bar, which you can observe here. Dewey bar's luminosity in ice cube can go fluctuate up and down to a large extent uh, if this actually happens. And indeed, no, if you want the oscillations, you will always take a Fourier transform. And these people have shown that a Fourier transform can actually show a peak to you, and that peak and the strength of this peak will also depend on the mass of the star. Okay? So looking at neutrinos will therefore tell us what was it that made the star explode, whether they indeed were such instabilities, and if there were instabilities, uh, how did they explode the star, what was the frequency, how did the star oscillate. Okay, so indeed these things can be seen quite easily. Okay. So, in short, uh, if you look at a single supernova, just one single event, right? Only 10 seconds. So this is what 10 seconds of observation will tell us about particle physics. They'll identify mass ordering. Uh, if we see neutralization burst and suppression, they'll tell us whether the ordering was inverted or normal. We may be able to see shockwave effects. In this case, it will tell us where the shockwave was and whether the hierarchy was normal or inverted. Similarly, about earth matter effects. And they will tell us about collective effects and about instabilities in flavor conversion. This was all about particle physics. Okay. But on the other hand, they will also tell us a lot about neutrinos themselves. So we saw that it will allow us to point at the supernova uh, many hours before it is actually seen. Um, then if we can look at the shock wave, then we can actually see that shock wave traveling in neutrinos by looking at these neutrinos and see where it was at various times. Uh, we can look at the SASI instabilities, okay, which will help us understand the mechanism of explosion better. It will also allow us to look at possible QCD phase transition. And if we understand all of these things and figure out what is the ordering of neutrinos and whether shock wave propagated or not, the earth fits are there or not, we can trace backwards and figure out what are the primary fluxes of neutrinos, initial levels that actually started from, what are the energies, what are the luminosities. Okay, so whatever I showed in my first two slides today, the predictions from computer simulations, we could confirm them, and therefore we could confirm our understanding of inside of a star. So remember that even for a star as close as the sun, as Professor Murthy explained to you, took us a few hundreds of years to even try to understand the physics of it, to actually understand how the sun shines. Here, of course, in those 10 seconds, we will learn something about it, no, not entirely, but some very, very significant information will come out of those 10 seconds. Okay. Any questions about this part? Let me keep this in front of you for maybe a few seconds, and then I will go to my last topic.
Amol, you have 5 minutes.
Yeah, that's fine. Okay. So all of this was by one supernova explosion. Okay. However, since billions of years, a lot of supernovae have been exploding in the universe. Okay. And when supernovae explode, they give you neutrinos of all species. And these neutrinos just keep on traveling in the universe because there's nothing to absorb them. As a result, all around us, actually, even the Earth is floating in a sea of neutrinos. Okay. Of course, there's a sea of neutrinos that started at the Big Bang, which are very low energies. But there's also a sea of neutrinos which came from all the earlier supernovae, which gave out lots of neutrinos. I mean, 10 to the power 58 neutrinos per supernova. And there have been literally, I think billions is too short word to say for this. Billions of supernovae which have happened in our universe so far. Okay, and because of all of them around the Earth, there are a lot of so-called supernova relic neutrinos. One of the aims of supernova neutrino detectors is to have a look at them. Okay. These neutrinos have energies around, well, between 0 to 40 MeV or so. You can see this spectrum here. However, at lower energies, let's say less than about 12 MeV, you cannot see them because the antineutrinos from our reactors overwhelm. Okay, they are thousands of times more than what the supernova relic neutrinos will be. So you don't expect to be able to separate them from reactor neutrinos if you are less than about 10 eV. On the other hand, if you go to slightly larger energies, there's a background due to nu E bars in the atmosphere or nu mu bars, which also convert into E bar from the atmosphere. What this tells you that it is also not possible to distinguish them from nu mu bar and nu E bar at higher energies. However, there's a small energy band which is between about 10 to 20 MeV or so, it's mega electron volt, where you could see these supernova antineutrinos. These plots are plots made for a water chemical detector like Super Kamiokande, where you have added gadolinium so that whenever this inverse beta decay reaction happens, you will be able to immediately see that a neutron has come out. Okay, this detector is well, the proponents called it Gadzooks, and it had a nice full form which I currently do not remember. Okay, but this is just to say that apart from individual supernovae, we can see the effect of all supernovae which happened in the universe for last billions of years, and that's what we expect to see. Uh, the current water chemical detectors, in fact, do aim to see this and try to reduce their background and see if we can observe them. Okay, these predictions depend on shock waves and collective effects, but let's not go into that right now. The fact that we'll be able to see some of them already is an exciting possibility. So we are at the end of my series of 3 talks, and as usual, I will leave you with questions for thinking. So one question is, what kind of detectors do we need to build? Okay, we know what detectors we have, but maybe one of you can come up with new ideas that people haven't thought about. The detectors which can find out complementary information about what we have learned so far. Second question is, what do we need to understand theoretically to be able to extract maximum possible information from these 10 seconds of many neutrinos that we will see? And one of the major answers here from neutrino side is the collective effects, nonlinear ones, which are not fully understood. Uh, the third question would be, how would they affect supernova explosion? Because we know that if they oscillate inside the core, supernova explosion may get affected. Understanding this would need cooperation of astrophysicists as well as particle physicists, which is actually happening. Okay. And then there is a sort of a 1 crore rupee question, maybe 1,000 crore rupee question perhaps, which is, when would the next supernova happen in our galaxy? Okay. So remember, the 87 supernova did not happen in our galaxy. It was happened in the Large Magellanic Cloud, which is nearby. The last supernova observed in our galaxy actually happened a few hundred years ago. It was observed by Kepler. So it was definitely very long ago. It is normally expected a supernova happens in the galaxy 2 or 3 times per century, if you look at our galaxies, but somehow we haven't observed them yet. So maybe it is time for us to observe them sometime soon. And if we are lucky, then we will get all these things that we saw in the last 1 hour also. More exciting things will, of course, come in the next lecture, which will be given by Professor Schulberg. But at least what I have done is given you a sort of a more hopefully intuitive way of understanding how supernova neutrinos will help us understand this. Yeah. So I will stop now and I will have a look at these questions. There's one question. What about INO project and what methods are used? INO project uses ion plates, and the neutrino interaction ion plates produces a muon, and this muon propagates and bends under magnetic field in the detector. Okay. Uh, the INO project is mainly meant to look at muon type neutrinos, which energy is more than 1 GeV. So for supernovas, as far as supernovas are concerned, I know definitely will not see individual neutrinos over supernova. Okay, as was mentioned earlier in some of these chats, it is possible to look at reactions on iron nucleus to see whether we can get 1 or 2 extra neutrons, but that is not exactly the main aim of INO. The main aim is different, but of course it can play a role as a complementary detector to see if we can see something extra anyway. So even if we did not build it for supernova neutrinos, maybe we'll be able to say something. We'll be able to say something about supernova neutrinos. Work on that has been done in a few cases, but yeah, we need to do more work on that. The question by Professor Datar: what is the ratio of failed to successful supernovae? And the answer actually is we do not know, because we do not know failed supernovae. See, you will not know a supernova has failed unless you see neutrinos coming from them. Okay, and at least we know that in our galaxy, in last about 35 years, as far as we know, there was no failed supernova. Because if there was a failed supernova, then we would have observed it in neutrino detectors. Okay, so as far as I know, that has not happened yet. Okay, so unless we run for a very long time and look at neutrino, look at number of supernovae that give us neutrinos and not light, and number of supernovae that give us the neutrinos and light, then we'll be able to figure out what this ratio is. Okay, otherwise we will. There's no other way of finding out what is this ratio. Okay, so yeah, so there ends what I wanted to say. So if there are no questions, then we can actually stop. And okay, so let me see this. There's a one question which says, yesterday's class you told us that quantum mechanics works at large scale. Does it mean uncertainty in that process? Of course, see, everything that happens in the world is quantum mechanical, although we don't easily see it. So yes, indeed there is uncertainty. The
I
reason,
mail.
sorry, uh, the point at which this enters is the following. So remember that we said that electron neutrino, if you produce it, it does not have a fixed mass. Its mass can be either m1 or m2 or m3, because electron neutrino is in all these three mass angle states. Okay, uncertainty allows this to happen. Uncertainty principle allows a neutrino to have any one of these three masses. Okay, and that's where this enters into picture. Quantum mechanics allows an electron neutrino produced inside a sun, let's say, or a supernova, to be in all these three states simultaneously. Okay, because its energy is not cannot in principle be perfectly well measured. Okay, and that is what allows you to also. Yeah, nice question.
Thank you, Professor, for this informative session. For the next session, we have with us Professor Kate Skolberg, and the topic is Imagining the Next Galactic Neutrino Blast and an idea of the data next one will bring. I welcome you, madam, on behalf of the organizers. Over to you, madam.
Thank you. Thank you very much. Okay, let me try to share. Okay. And let me go to full screen. Okay, so I'm going to follow on from that beautiful lecture by Professor Dige and tell you more about the detection side of things. So what we're actually going to see in the detectors, I heard about that somewhat, but I'm going to focus a little bit more on that and zoom in on some of the aspects of the observations that we will get. And so here is what I'm going to talk about. I'm going to focus a little bit on new things that have been happening in the last few years, and some advances in ideas for new detectors, and that's one of your topics to think about. So that's there are new things coming. So I'll tell you first, I'll do a recap of some of the things you've actually already seen in the past lectures, focusing on the experiments. I'm going to talk about how we can expand our sensitivity to the different flavors of the neutrino burst. That's actually a feature of the supernova flux, is you get all of the flavors of neutrinos, and how can we actually pick apart the pieces of it? How can we actually detect the particular components? And then I'll say something about some future prospects, and I'm going to take a little bit of a diversion into an experimental effort that will improve the interpretation of the supernova data. Okay, so this is just a recap. I think I showed a similar slide in the first talk. This is just a recap of what happens. You get this huge burst of neutrinos of all flavors and a compact remnant coming from the collapse. This happens rarely in our lifetimes, but fairly often in the universe. And we expect inside our radius here, we expect maybe 3 or so per century. So these are rare, but it means it's very important to capture all the possible data. Now, you saw something like this before in Professor Dige's talk. The information that we're after coming from the supernova that we can get at experimentally is in the flavors and energies and time, this profile of the burst. And so this is an example of a particular model, which is kind of typical for what you expect. The top plots here are showing the luminosity as a function of time. The bottom are showing the average energy as a function of time, and the different lines are showing the different flavor components. So you have electron, antineutrinos, and then the other flavors, the heavy flavors and the antineutrinos. So the arrows here are the vertical lines here, where you have the early time, which is up to about 50 millisecond. That's when you get this really super intense blast of electron neutrinos. That's the solid line. Here you can see them turning on as there's an infall. There's what I call a trapping notch, which is when the density of the protoneutron star is so high that the neutrinos themselves are trapped, and there's a little bit of a dip in the luminosity. Then you get this famous gigantic burst of electron neutrinos called the neutronization burst, or the deleptonization burst, which is when the neutrinos coming from the protons and electrons getting squished together to make neutrons, those are really released by the shock. Then in the next scale, there's some of these phenomena that you heard about in the last talk. There's the SASI, that's a standing accretion shock. That's where the star kind of rumbles and oscillates. And then there's the explosion, and there can be interesting features in the signal reflecting that, also shock waves, as you heard about. And then the last 10 seconds, which is actually the bulk of the neutrino flux, is cooling. It's when you get all 3 flavors and they become similar energies. And that happens over 10 seconds or maybe a few tenths of seconds. Actually, it goes a bit longer than this. It's actually a disadvantage. A lot of the really expensive supercomputer simulations that determine, that give predictions for these fluxes, they only go out to about 10 seconds. And in fact, there may be very interesting things happening later. We heard a little bit about that from the last talk as well. And so this is the cooling. And this is also the generic feature that you heard about quite a bit, is that in general, the electrons, at least especially in the early times, the electron neutrinos are cooler. They have lower average energies. And then the next highest energies are the nu bar, and that's and then you get the highest ones are the other flavors, and this is a kind of a very general physical argument. It's because the mu and tau flavors have fewer interactions with the matter, and so they decouple from the star deeper inside, which is where it's hotter, and so they're hotter. The electron neutrinos have the most interactions, and therefore they decouple where it's cooler. And this is, of course, not completely true. It's a kind of an approximation, especially in the late times, the energies become more similar. And of course, flavor oscillations do all kinds of crazy things to the signal. You heard also a lot about that. And that is a modification of the spectrum, both modifies the energies and the flavors as a function of time. And so there's very complex and interesting phenomenology that we can measure in the signal. And here's a picture just of some generic expected spectra for different flavor components. And here again, you can see the general hierarchy of energies. And this is a kind of general description of how this functional form will describe the spectrum for most flavors to a reasonable approximation. We call that either quasi-thermal or pinched spectral form. Also, Garching parameterization is what it's sometimes called. That's the group that I guess first came up with this. And so this is the electron neutrinos are red, so they're the coolest, lowest average energies. Here are the electron antineutrinos, and then this is the sum of the other flavors, and I'll call these other flavors nu x. And so this is just a typical kind of spectrum. You can see the peak here is a few tens of MeV. So it's like 10 MeV, maybe up to 20 or so, depending on the flavor. So that's what this looks like. This is another visualization of the fluxes as a function of time and energy. And this is the observable, this is what we're after. This is the underlying truth that we would like to measure with our detectors. And the top pink ones are the electron neutrinos. And here, this y-axis is the energy. This is the time on the x-axis, and the color scale tells you the something proportional to the flux. This here is electron antineutrinos. And then this is the other four flavors in the gray grayscale colors here. And so you can see how this evolution happens. These are different time scales. And so here you see the bright neutronization burst in electron neutrinos, and then the slow cooling over 10 seconds in the last set of 3 vertical panels here. And here's another example, and this is a different model, but this is a model where, in fact, there might not be a big visible supernova, but there could be a black hole formed. And in this case, what you see is that it's actually a high flux for about 2 seconds, and an increase in energy in the last second or so, and then an abrupt cutoff when the black hole forms. And so this is something you can see that there's, this white means nothing after about 2 seconds. And that sharp cutoff is something that we would be able to observe in a neutrino detector. So we could actually see that black hole being formed in real time. So you've also heard a lot about this. This is 87A. And I just want to point out that this was 2 water detectors that saw the burst of neutrinos from 1987A. And I just want to point out here that these were almost all electron antineutrinos, since that is what the water detectors are sensitive to. There was also a couple of scintillator detectors. Those are also sensitive to nu bar. So that signal was really only one component of the flux. It was only one flavor out of the 6. And so that's something where, that was extremely exciting, but we basically have no measurements of those other 5 flavors from the flux. And so that's something that the future we are hoping to get a broader flavor sensitivity. And so that's what I'm going to talk about. I'm going to emphasize that in the next. Okay, and we heard a gorgeous talk from Professor Dige in the last hours about what we can learn, and that's both the core collapse physics and the neutrino physics. And these are kind of a virtuous circle, in that the more you know about the core collapse physics and the better your observations of the supernova, the better you can constrain neutrino physics. And it also works in the other direction, that if you have better understanding of the neutrinos from terrestrial experiments, measuring neutrinos, then that helps in interpreting the astrophysics. And so this is really something where you put a lot of information together coming from different fields, from astrophysics and particle physics, to get the best understanding of the phenomenon. And gravitational waves may also play a role here. And you heard also about the early alert, that also the neutrinos, the fact they get out very fast will help astronomers in finding the observable electromagnetic radiation as fast as possible. Okay, so let's talk about what you need in a detector. And this is the wish list, that if you're an experimentalist, these are the properties of a detector that you want to consider when you're trying to build a detector. So first of all, you need a lot of detector mass, just because of the low neutrino cross-section. Even though the burst is incredibly bright, it's still a low event rate. And you need about 1,000 tons of detector mass for about 100 events. That's just the back of the envelope order of magnitude. And so we're talking about, where here event, I mean one neutrino interaction. So we're talking about huge detectors. You have to be sensitive to the energies of neutrinos, which by neutrino standards, these are relatively low. So a few MeV, you want to have sensitivity to quite small energy depositions. And so that's challenging. That's less than, for example, from a beam, it would be typically a GeV, so 1,000 times more. So you're looking for small energies. You want to have good measurement of that energy. You have to be able to resolve the features in the spectrum if there's interesting things happening, wiggles from oscillations, all those kind of things. You want to be able to actually measure that. You also want angular resolution. You want to be able to tell where the neutrinos are pointing from. And you heard a little bit about that in the last talk. I'll say also a little bit more about that. You want to try to exploit the neutrinos that remember where they came from. Not all of the neutrino interactions are directional. Not all of them have good information there. You also want to measure in real time. You know, it's a very short time scale thing. It's 10 seconds, and you have features that are milliseconds. And so you want to be able to time the neutrino interactions that come in. And so that's another thing you have to try to make sure your detector can do. You want to have a low background. Of course, you want the background rate of radioactivities and cosmic rays and things like that. You want that to be less than the rate in the burst. And that means that you usually want your detector to be underground. And that is hard, that adds a complication to actually put the detector underground. I put this one in yellow since it's so important for the physics. If possible, you want to have you want to be able to tell what the flavor of the neutrino was that came in. And that's a hard thing to do experimentally because of the physics of the interactions. So you want to be able to tag the flavor components. And then also, because these things are so rare, you want to have a detector that it has to run for a long time, and it has to run most of the time. If you have a detector that only runs one day a week, you have that would be terrible if your supernova happens on Tuesday and you're only running on Wednesday. So you have to have a high uptime. And this last thing is a kind of a difficult issue, because if you have to wait for 30 years to see a supernova, or maybe 50 years or 100 even, then it's hard to convince a funding agency to give you money to build a big detector. And so there are very few detectors around that have as their only purpose looking for supernova neutrinos, just because that's too hard to find funding for. Nobody wants a payoff that might be 50 years away or 100 years away. And so for that reason, a lot of the detectors that are built really have some other purpose. Okay. Some reason, there we go. Okay, so let me just recap now. How do neutrinos actually interact with matter in this energy range, or in general, in fact? So there's really two kinds of neutrino interactions. There's charge current, and the feature of this is that the neutrino has a particular flavor, and the final state, lepton, so this lepton is an electron, a muon, or a tau. This lepton has the same flavor as the neutrino that came in. And so this allows you to tag the flavor of the neutrino. If you can observe this lepton and measure it in a detector, and you know if it's an electron or a muon or a tau, then you can tell that the neutrino that went in was an electron or a muon or tau. And so these are very valuable for trying to understand the flavor composition of a neutrino flux. And the other thing about this, of course, and this is always true, that the incoming neutrino has to have enough energy to make the rest mass of the final state lepton. And so an electron is light, so you don't need that much energy. If you're an electron neutrino, you only need about an MeV or so to actually create a lepton in the final state, to create an electron on the scale of an MeV. But if you're a muon neutrino, if you actually want to make a muon in this kind of charge current interaction, then you have to have more than 100 MeV because muons are heavy. And so that's the problem, is that if you're a muon neutrino, you can never have a charge current interaction if you have, say, 50 MeV, because you just don't have the oomph, you don't have the energy to create the rest mass of the muon in the final state. However, there are interactions that do have, that can create particles in the final state that are observable even if you're less than, say, the mass of the muon. And these are neutral current interactions. And these are proceeding by exchange of a Z boson. And these can be, for example, scatterings. And those don't have a threshold, so they can happen at any energy. But the feature of a neutral current is that they don't care about the flavor of the neutrino. And so all neutrino flavors will have neutral current interactions at the same rate. And so that's a way to access neutrinos experimentally that are below the threshold for making a charge current interaction like this. And that's a valuable tool for supernova neutrinos, but the rates tend to be low. Okay, so now here, let me go through the kind of interactions that happen in detail for neutrinos at energies of supernova bursts. So here I'm going to divide these into charge current, where it cares about the flavor, and neutral current, where it doesn't. And so you can have this is the simplest kind of interaction you can have. You can have a neutrino that comes in and smacks an electron, and that can actually happen either by charge or neutral current means. For neutral current, it happens for all of the flavors of neutrinos. For charge, only for the electron flavor neutrino, and that turns out to be the highest rate. And this is actually pretty small probability. You can say neutrinos are, electrons are kind of small targets. So you have a low rate per electron. But this is actually it still happens, and it's quite a significant interaction for supernova neutrino detection, because this is a directional interaction. The neutrino comes in, it smacks the electron. The electron actually remembers the direction it was kicked from. And so if you can determine the track that the electron is following, you can then point back to the supernova. And I think Professor Dige showed a plot of that, and I'm going to say more about that in the rest of the talk. And so this is very useful for pointing back to the supernova, even though it happens at a relatively low rate. Okay, so now the next most simple target is a proton. And that allows a detection of neutrinos, antineutrinos, electron antineutrinos, by their absorption on protons. And that makes positrons, which is a particle where you can see the energy loss, and also neutrons. And the neutrons can be captured and make gamma rays. And that happens with the time delay. And in fact, this is a very important interaction. This is actually how neutrinos were first observed. This inverse beta decay is there's a delayed coincidence between the positron signal and the capture of the neutron. And that's a very powerful tool, because if you see those two signals happening close to each other in time, then you have a good, that's not just a background, that's really a neutrino. So this is very, very important for neutrino detection in general, and especially for supernova. And protons are common. You can make, they're common in water, which is cheap, and in scintillator. And so those are good detector materials. You can also have elastic scattering, which is neutral current. Neutrinos come in, smack a proton, and the proton recoils. And this also, there's some directionality there, not actually, it's hard to exploit, but it's there. And this allows very, very low energy, or gives you very low energy recoil. So it's more challenging to detect. So it has a fairly high cross section. So it's kind of like hitting a bowling ball with a ping pong ball. It's kind of easy to do, but that ping pong ball or that bowling ball doesn't recoil with a lot of energy. So that's the but it's still a possible interaction to use. Then you can have neutrinos interact with nuclei, which can be big or small, and you can have charge current interactions where the underlying interaction is with a proton or a neutron inside the nucleus. And the observable for charge current is you get an electron or a positron, whether it's a neutrino or an antineutrino, we'll tell you whether it's electron or positron. And then you can also get stuff that gets emitted from the nucleus that gets kicked out. You can get protons or neutrons that are ejected. You can also end up with an excited state nucleus, and it de-excites, giving you gamma rays that you can observe. So there's can be a bunch of debris coming out as well that in principle you can observe. And so that's, so this is another possibility. And you can also have, and so if this is like a ping pong ball hitting a larger ball, this is like a ping pong ball hitting a boulder. It's a coherent elastic neutrino nucleus scattering where you have a neutrino come in and it recoils off the entire nucleus, and the nucleus recoils away with a very tiny amount of energy. And that's also neutral current, and it's also potentially observable. And I'll say a bit more about that as well in the later part of the talk. And I'm going to highlight this one in yellow because it's very important for current detectors, which are mostly sensitive to nu bar. That's actually why the 87A was almost all electron antineutrino, because those were water and scintillator detectors where inverse beta decay is dominant. And just to emphasize here that the threshold for charge current is very important for supernova neutrinos. And so here, this is I've got now a log scale x-axis. These are the spectra that you expect for electron neutrinos in red, for electron antineutrinos in black, and in green is the other flavors. And you can see they're all less than 100 MeV. So there might be a tiny tail greater than that, but it's really all less than 100 MeV. And the thresholds for these interactions to go, so for elastic scattering, there's no threshold, but if you want to have an interaction on a proton or on nuclei, there's a threshold for that to happen. And that means that you can't see some of the flux. And so, for example, inverse beta decay, you can see all the energies above this vertical line. So that's most of it. For argon, you can see all the energies above this line, and that's, you cut off the low energy tail. And for oxygen, it's even higher. But if you want to see muon and tau neutrinos, you actually have to create a muon or a tau. Actually, tau, you need 3.5 GeV, so that's crazy. You'll never see that. For muon, you need 100 GeV, 100 MeV, a bit more than 100 MeV. And so that means that you really can't see muon and tau neutrinos using a charge current interaction. You really need to have the neutral currents in order to have access to basically 2/3 of the flux. And so that's a property of neutrinos that we have to fight in order to get good information from a supernova neutrino burst. Okay, so here, this is an overview of the kinds of supernova neutrino types, and you've already seen some of this. There's water detectors, and here I'm putting the flavor where there's the most sensitivity that is dominant in that detector. And so for water, it's almost all nu bar on the protons in the H2 of the H2O. There's also long string detectors that are based on water. So in ice and water, there are these long strings of phototubes that are looking for a kind of overall glow of a signal from mostly inverse beta decay, so mostly nu bar. And so these kind of long string detectors don't detect single events, but they detect an overall time profile for mostly dominated by nu bar. Then there's argon, which is mostly sensitive to nu E. So that's a distinct thing from the other. And I'm going to say more about that. There's scintillator detectors, and that's hydrocarbons. And so those also have free protons. And so those are also primarily sensitive to nu bar. There's a couple of lead-based detectors. There's one lead-based detectors and some proposals for others that's also mostly sensitive to nu E. Those tend to be small detectors, and detectors of this type of iron also could, in principle, have a similar interaction, but these are relatively minor. I'm going to talk about dark matter detectors, which are sensitive via coherent elastic scattering to all of the flavors of the neutrino flux. And so what we're trying to do as experimentalists to get at all the glorious phenomena that you've heard about is, what we're trying to measure is this underlying neutrino flux. On the left-hand side, these are the three flavors as a function of time. This is the truth observable we're trying to measure. And so we have access to this by these NUI and the NUI bar. We have access to that by charge current interactions that are sensitive to NUIs and NUI bars respectively. All of them are sensitive to neutral current interactions. But in practice, we can't measure with great precision. We're restricted by the physics of the interactions. And so we have, not only are the detectors imperfect, they have imperfect resolution, but the interactions impose a fundamental limitation on how much information we can get out. And so we have to be as clever as we can to get the best information out. And so this here on the right-hand side, these are distributions of what you would actually observe in the different detectors. And so, for example, here, this top one is what you'd see in an argon detector, which is mostly Nu-E. This is what you see in a water detector. You can see some of that neutronization burst, but mostly it's Nu-E bar. And then for scintillator, this is what you'd see. You'd also see some of that neutronization burst, a little bit of it, but you get also some neutral current interactions, which are sensitive to the entire flux, but you get only you get 15 MeV gamma de-excitation. And so that's, you can't see a spectrum. You just get kind of one bin in energy. And so what we're trying to do, there's also subdominant channels in each of these detectors. What our job as experimentalists to do is to gather that data and figure out how can we go backwards, given what we observe, how can we figure out what the best approximation of the original fluxes are? And so that's the job of the community, of actually experimentalists in collaboration with theorists, is how can we unfold the fluxes? How can we get the original truth of what the neutrinos are coming out from the observed signals? And experimentalists, we have to understand and optimize the detector's response to the neutrinos. Okay, so I'm going to organize the rest of this by flavor to try to point out what the dominant, for the three different components, the Nu-E bar, the Nu-E, and the Nu-X, which are kind of the three observable flavors. Of course, the Nu-X, you can't distinguish between the mu's and the tau's, and so you have to put them all in one bin. I'm going to go through each of these flavor categories and talk about what is what we can pull from them. So Nu-E bar, as I mentioned before, is primarily what inverse beta decay measures. It is what inverse beta decay measures from the flux. And water Cherenkov detectors and long string detectors and scintillator detectors are all going to be dominated by this signal. And you've heard already quite a bit about Super K. The upgrade to that will be Hyper K, much bigger, much more statistics. For the long string type of water detectors, there's Ice Cube at the South Pole, which will see this glow in the ice from all the primarily inverse beta decays in the ice. And then there's ideas for new, bigger detectors, both at the South Pole and also in the Mediterranean. There's one called KM3net. And for scintillator, there's actually a lot of kiloton scale scintillator detectors. Snow Plus is turning on now. In fact, I think they're filling with scintillator right now. And then there's this Juno detector in China, which is 20 kiloton. And so that also has a really bright future for getting huge Nu-E bar statistics. So some of the other detectors like argon will see some Nu-E bar, but it's much less. It's only at the percent, probably 5% level. Okay, so now let me talk about Nu-E. And this is actually one of the things I've been personally working on quite a bit recently. And so this is the dominant channel in argon and lead. It's subdominant in water and scintillator. Water and scintillator get some. But detectors like Microboon and SBND at Fermilab, and then Icarus and Dune, which I'm going to say more about, that's really what the main signal is going to be. It's going to be Nu-E. It's going to be electron flavor. I can mention, I did mention briefly, and I think you heard in the last talk, there's also a detector called Halo, which is sensitive to, it's made of lead, It's actually made of old detector components recycled from the snow detector. And that would get a modest signal. It's only about 80 tons, so it's a small detector. There are ideas for upgrading that to be much bigger for the future. And then INO, which is iron, would also possibly see some signal from ejection of neutrons also in iron, although iron is much lower cross-section for ejection of neutrons than lead. And here's just a little bit more about that. Here's halo. So this is the interaction, is the neutrino comes in, it creates an excited state. So you actually don't see this electron, but what you can measure in a neutron detector is either 1 or 2 neutrons. And 2 neutron events have on average higher energy than the 1 single neutron events. And so you can learn a little bit about the spectrum from looking at the ratio of single and double neutron events. So this is a ongoing it will be a modest signal, but there are possibilities for the future. Okay, so now let me talk about argon, which is what I've been putting a lot of time in personally recently. So there are several instances of detectors that are called liquid argon time projection chambers. And these are, the idea here is that you are actually looking at tracks. You're looking at fine-grained tracks coming out of the final state of an interaction. And these are actually built mostly for accelerator neutrinos. But so the idea is here, if you get a particle and it deposits some energy, if you have some sort of interaction that's happening and you get charged particles that are depositing energy via ionization along their tracks, you have a big volume of very pure argon with a very large electric field across it. And those, the ionized charge, the electrons coming from the ionization will drift along the electric field. And then you will get a projected image of that track in 2 dimensions that you can pick up that charge on collection and induction planes of wires or possibly other kinds of readout. And then from the time that drift takes, you can tell the 3rd dimension. And so you get a 3-dimensional reconstruction of a track. And so this is a very, very cool idea. And you can get very precise images of what the final state particles are. So in this case, if you have an interaction of electron neutrino with argon 40 that makes an electron, you can actually see the track of the electron. And then if you have an excited final state of potassium, it's going to spit off some gamma rays, which then make little blips in your detector. And so you get this kind of image of a final state, the debris left over by a neutrino smashing into an argon. And you can really see everything about that track with high precision using one of these tracking chambers. Now, of course, in real life, it's hard if you're an experimentalist, but this is the idea. And so here, these are the instances of these detectors. There's the Icarus detector, which has actually just been moved from Italy to the US and is turning on in the US at Fermilab. There's Microboon at Fermilab, which has been running for a while. There's SPND, which is turning on soon at Fermilab. And then the Dune detector is 40 kilotons. So these are all modest size. These are less than 1 kiloton scale. Dune is a huge 40 kiloton scale detector. And so this is going to be in South Dakota. And its day job, its main purpose is actually to look for neutrino oscillation properties, in particular CP violation and mass hierarchy, using those beam neutrinos. So here, this is where the underground lab is. The accelerator is at the Fermilab. It's a 1,300 kilometer baseline, and it's very deep underground, very cosmic ray quiet location. There's actually different options for the modules. In fact, there's now currently a new option where the charge gets drifted vertically that is under consideration now. And you detect not only the charge, but also scintillation light that comes from the interaction. And so these, it's a kind of dual mode detector where you can see the ionization and you can also see the light coming from the same interaction. And so this is lots of work underway for this. And the aim is to have the first underground module this decade. And supernova burst, it's I said the day job was the long baseline neutrinos, but in fact, it's the supernova burst is in the list of primary physics goals. And so it's an important capability of Dune to be sensitive to a supernova burst. So this is what you would see. This is an example of a model. And here is the different flavor composition as a function of time. This is without any oscillations. And actually, oscillations are important. And so here you can see these different phases. You see this very bright neutronization burst. And this is, oops, there we go. This green shows the electron flavor component. You can see it's dominated by that. There's a little bit of elastic scattering, maybe a tiny bit of the Newey bar, but it's really almost all electron flavor. And this is, if you integrate over time, this is the spectrum that you would observe in the detector. So this is very interesting. I think you saw this plot also in the last talk. What I showed you here is without flavor transitions, with no oscillations. In fact, there is likely to be a very large effect from flavor transformation inside the supernova. And you could see there's a very strong effect. And it depends on the neutrino mass pattern. And this means we have a way of getting at the question of neutrino mass ordering. And you can see you get a suppression in this neutronization burst for inverted hierarchy and a very strong suppression in normal. And so this will be really important information on neutrino mass ordering. I put a question mark here since it depends on the model a bit, how well or how clear the signature is. And that's something we're studying now, but there's clearly information in that flavor composition as a function of time. And what we're trying to do is we're trying to figure out now, so there's a lot of work, we've made actually a lot of progress recently on how can we actually extract information, how can we actually figure out if this is the kind of event we have, and how can we get the energy of the neutrino, and how can we point using these events. And so we have, this is a simulation, this is showing the truth. For example, of an event like this where you get an electron, but you also get some gamma rays. You can also get other things like neutrons popping out. And this is what it would look like in event display. Here's a little track. And so these three views correspond to different wire planes. So they're kind of three different views, projections of the event. And so this is the electron track, and then these little blips are what you get from gamma rays that come from de-excitation. Here's just another example of how different kinds of events, different interaction channels would look different in Dune. And so here's another example on the right-hand side of this kind of charge current interaction where you have an electron neutrino. So you see this little worm, which is the track from the electron, and then these little blips are de-excitation gammas that come from that are Compton scattering the detector and leave little chunks of ionization. In contrast, on the left-hand side, this is what you'd get if you have a neutrino that just comes in and kicks an electron. It just makes a single clean electron track. And so what we're trying to evaluate now is how well can we, in practice, tell the difference between this left-hand side one and this right-hand side one, which will be very important for interpreting the signal. And this is, maybe I'll skip that. This is just showing for a given neutrino energy, what the distribution of energies that we get out are, and we can actually get a much tighter distribution if we use both the photons and the ionization. And this is a kind of bottom line plot of how well can we actually measure that spectrum for electron neutrinos. And so here, this is another showing you the parameterization that we have of how do you describe the spectrum of neutrinos. And it turns out this is a reasonable approximation. And so if you have an example where this is our truth parameter, so you describe it with three parameters, there's a normalization, which tells you about the total luminosity. There's an average energy, and there's this parameter called alpha, which is called a pinching parameter, which tells you whether you have a narrow tail or a wide one. And there's the truth here for this particular example is at the star, and what these regions show you are what we would be able to constrain if we actually had a burst in Dune at 10 kiloparsecs, and these dots are models. And so you could see you could constrain the range of reasonable models describing this. And this is really just one aspect. And how does it change if we have a more nearby supernova? You get more statistics, and so you can do a better job. And so here's an example of this parameter space where you can see if you have a nearby supernova, you get better statistics and you have a smaller region. If you have a different detector resolution, it turns out that's actually not a huge effect, but you do better if you can actually improve the resolution of your detector. Now let me talk about pointing a little bit. And so here's another, just showing you the picture of the electron. And that electron is kicked in roughly the direction that the neutrino is coming in. And so if you can reconstruct in 3 dimensions where that new electron is going, you can tell where the supernova is. There's actually a kind of unlike a Cherenkov detection, you saw that plot with a Cherenkov. If you have a Cherenkov ring, it's a cone, and that tells you whether it's going forward or backward, you can tell the hemisphere. But if you have just a track, you can't tell if it was going forward or backward in a detector like Dune. And so you have to do some tricks to try to figure out if it was going forward or background. And it turns out there's information, more subtle information in the signal. And so these are examples of studies showing the angular resolution. So this is for the neutrino direction. It's something like 50 degrees. So, I mean, that's not that great for a single neutrino, but if you put a whole ensemble of them together, it turns out that it's really quite good. If you statistically observe, let's say, a couple hundred elastic scatters from a supernova, you can put that whole sample together and determine to only a few degrees the direction to the supernova. And so here's an example. This is the true supernova direction. This is using the ensemble events. This is where you can, this is where the best fit is. And this plot here shows you the cosine of the angular difference. And it turns out to be good to something like 5 degrees. And so that's very promising. We can actually also use the other charge current interactions, which have a little bit of an anisotropy, but there's a lot of them, so we can use those as well. Okay, so that's electron neutrino. Let me now talk about the other flavors, the so-called, some people call them heavy flavor neutrinos. That's not really quite right. But the idea is to use neutral current to tell us about those other, the nu mu, nu tau, and nu mu bar, and nu tau bar, the other ones. And those are more likely to have a higher energy, so that helps a bit. And these are, they are observable in water and scintillator. There's a 15 MeV gamma in scintillator. There's also possibility for looking at them in argon. That's something we're also looking at in some detail. The nuclear theory is actually hard for that. And then there's also the coherent elastic neutrino nucleus scattering, which turns out that's quite promising for getting studies of the entire flux of the neutrinos. And so here, just to put these in these categories here, in current and future scintillator, there's the 15 MeV gamma, argon, also some possibilities. And then these very large dark matter detectors, even though they're much smaller than the standard supernova detectors, they still have, they're coming now to a scale of tens of tons, where you actually get a pretty reasonable rate of neutral current coherent elastic scatters. And so let me say a little zoom in more about that. This is also something I've personally spent a lot of time on recently. So the idea is that the neutrino comes in, it smacks the entire nucleus as a whole by exchange of a Z boson, and then the nucleus recoils. And what it means to be coherent is that the nucleon wave functions are in phase with each other. And when you have that condition, then the cross section goes as the square of the number of constituents. And compared to the single constituent cross section. And so you get an enhancement, you get a coherent enhancement that really gives you a higher event rate with respect to the kind of charge or neutral current interactions I was talking about before, the inelastic ones. And so these are examples of detectors that can exploit this kind of interaction. This is one kind of dark matter detector called it's also a time projection chamber, in that there's a drift of charge. It's not an imaging time projection chamber, but it does do drifting. This is an example for Darwin, which is a new generation 40-ton xenon detector. And this is the kind of event rate as a function of time that this kind of detector would expect, and really has very good distance sensitivity out to Milky Way distances. So these different colors represent different sizes of detectors. The green one is Darwin, that's the really big one. And so we're talking about hundreds of events as a function of time for a 10 kiloparsec supernova. And this allows you, this is really exciting because it gives you a measure of the total flux. The neutral current doesn't care what the flavor is, and so it tells you about the entire flux. And so this is an example of how well you could learn about the total energy emitted into neutrinos and make a measurement here of this. This is the same kind of parameter space that I talked about before, average energy and amplitude. And you can think of it, and so here's a plot for dark matter people. I don't know if you've seen this before, but this is if you are searching for WIMP dark matter, where the signature is just a tiny recoil in an underground detector, this is the parameter space that you use. And so you're looking at a cross-section for a WIMP over the mass of a WIMP, and these are the kind of exclusion limits that different experiments put. And there's a thing, they call it, in that business, the neutrino floor, and that's the parameters at which you would get a background from natural neutrinos. So natural neutrinos would be smacking into the detector material and basically drowning out any possible WIMP signals. And so if you are looking for very small cross sections of WIMPs, then after a while you get blinded by the sun, by neutrinos that are coming from the sun. And that's what this neutrino floor is. And that's a problem for dark matter detectors, but you can think of it as an opportunity for neutrino detection, because if you're in this range here, you get, if you have a burst supernova, this flux here, so this floor is set by the diffuse background supernova neutrinos that you heard about at the very end of Professor Digay's talk. These are the leftover supernova neutrinos that are infusing the universe and that create a background in this parameter space region for WIMPs. And if you have a supernova burst, that flux suddenly in 10 seconds increases by something like 10 orders of magnitude. So it's like this floor is coming up and it's smacking you in the face. And so that's kind of an opportunity rather than a disadvantage for these detectors. And okay, so let me say this. I just want to briefly mention some new things. And so these are ideas that are now getting discussed in June. And the idea is to actually kind of do sort of an ice cube style detection in a detector like Dune, making use of the sevens events. And so ice cube at the South Pole, I mentioned this, it cannot really see individual events because they only produce a few photons that are observable. But what they can see is kind of the sum of the glow of all the interactions in the ice that gives them an excess in their detectors over 10 seconds. And it's kind of, as long as your signal is greater than square root of n, you can observe this. And so this is what they're trying to do. And this turns out this should work very well in IceCube. And here the idea is to actually make use of sevens in a similar effect in a detector like Dune or maybe some scintillator detectors. And so here's now a plot. This is a very new plot showing these event interaction rates in argon and in scintillator. This is a log-log scale here. And so this green is the kind of electron-neutrino interaction I was talking about before. This is elastic scattering, but then you have this very huge rate of sevens. You know, it's a very high cross section, but you get these very, very tiny recoils that are very hard to see. And so the observable energy is very small. And it's kind of the same idea for scintillator. There's this kind of middle thing of proton elastic scattering. And so the idea here is to actually try to gather these photons. And it turns out that if you work out how many there are, it's something like maybe 10% of the total photons would be coming from the coherent elastic scatterers. And the idea is to try to figure out, can you actually get this glow? They're so small that you're not going to get individual events. You're not going to reconstruct tracks or anything, most likely, but you might be able to get these photons, which would tell you something about the total flux. And so this is in Dune here. The problem with this is that there's background that comes from argon-39, which is produced by cosmic rays in argon, in atmospheric argon. So the detector is filled with will be filled with argon that comes from the atmosphere. And that's full of stuff that is comes from cosmic rays hitting the atmosphere. And one isotope that's in there is argon-39, which is a famous nasty isotope there that produces about half an MeV-ish decay, beta decays. And so that is happening all the time. It's about 1 per liter per second. And so in a detector like Dune, there's lots and lots of these decays happening. And the half-life is long enough that you can't just wait for it to decay. It's going to be there for a very long time. And so you're fighting that. And so this is an example. This is a calculation here. This is the photons versus time from the glow. This is the charge current. It's a lot more photons, but then you have this kind of blinding glow of radioactivity. And so what we're trying to figure out now is how can we defeat this? And one possibility is actually use underground argon that was mined from underground where it has been sitting for a long time, and all of that cosmic ray stuff has decayed away. And so that's a promising possibility for this. But you need a lot of it, and it's expensive. And it's kind of the same idea for scintillator. I won't go through all the details of this, but here the backgrounds tend to be quite low, but the problem is that recoils give very low energy. So this is challenging too, but it may be possible, and it's something that we're excited about and looking into. Okay, and so if I have a bit more time, I don't know how I'm doing, I would just like to briefly mention this idea, which is something that I've also been spending a lot of my time on, which is actually to try to understand the interactions better using basically artificial supernova neutrinos. And here the idea is that if you have protons,
Hello, madam.
Sorry?
Sorry for interrupt. You have
Oh, sure.
5 minutes time. Is it okay,
Okay.
madam?
All right, I will zoom through this very quickly.
Yeah.
And so here is the idea is to actually kind of use artificial supernova neutrinos produced from pions decaying at rest, which give you a spectrum here. So this is a supernova spectrum in the solid, and then the dashed and dotted are the what you get from the source. And this is a plot of the flux as a function of distance. And if you're about 50 meters from this source, you actually get about a supernova's worth of neutrinos every day. And so we can use these supernova neutrinos to actually measure these interactions, which are very unmeasured, very unknown. And this will allow us to interpret the supernova when we actually get the signal. And this is where we are. This is at the spallation neutron source in Oak Ridge. And we have an alley called, we call it Neutrino Alley. And we have several detectors which are deployed there. And we have actually measured for the first time the coherent elastic neutrino scattering. And we're actually measuring lots of other things. But I will skip the details of this and move to the summary here, which are, this is a summary table. You don't have to look at all the numbers in it, but this gives you an idea of all the detectors that are running. And that in the green here, these are the near term or recently turned on detectors. These in yellow are the ones for the future. And so there's a lot of them, lots of events expected, especially in the future. So there's very exciting future for this. These are examples of the kind of signal you'd see as a function of time for these different detectors. For water, this is mostly nu E bar. This is mostly nu E. This is mostly nu E bar. And so there's huge information there that we can learn from. And these are event rates. And a question we got before was, what about Andromeda? We're talking about the galaxy. And so these are the event rates. This is just 1 over r squared, a function of distance to the supernova. And if you go to Andromeda here, you could see that something like Super K is going to get like maybe 1 event, maybe 1 event in Dune as well. It's the red line. But Hyper K could see maybe a dozen events. And so, that's about as far as we can go. And I showed this before also. This is just have to emphasize, this is a not competitive, it's cooperative. Basically, all of the detectors together are going to be improving the information of everything. We have this snooze network, which is putting everything together and enhancing cooperation. How can we get the most possible information out, including the pointing? In fact, another thing we can do is if we take the times of the signals that are arriving from the different detectors, we can actually point to regions on the sky where using that timing, where it will be more likely to find the supernova. So we can cooperatively improve the directional response of the network. Okay, so I will stop there and summarize of all the fantastic things we will get from a supernova neutrino burst observation. There's huge information to be had in the energy flavor time structure. We have to do our best to gather that information and interpret it. Detectors worldwide now have approximately sensitivity to the galaxy, maybe reaching beyond. What's going to happen in the future is expanding the flavor sensitivity. We're now mostly sensitive to nu bar. That's what 87A brought us. But now we're going to have a broader palette. We're going to be able to taste the electron flavors and have sensitivity to the entire flux via neutral current interactions. And there's actually subdominant things. If we have enough statistics, we should be able to explore as well. And we really need to understand how to infer the truth fluxes. We have to measure these interaction rates, these cross sections, to learn how to do a better job at that. We're also upgrading the early alert, and we have multi-messenger astronomy now, gravitational waves, all kinds of other things. And I think it will be a tremendously exciting event when we get the next supernova. So I will stop there. So happy to have any questions. And I hope I have transmitted to you some enthusiasm for what will happen.
Can you stop sharing, madam, slide? Thank you. Yes.
Thank you, Professor, for this wonderful and exciting talk. I now request all the participants to turn on their camera so that we can capture the screen grab.
Yes.
Thank you, everyone. Now we shall begin with the valedictory program. Science is the attempt to make a chaotic diversity of our sense experience correspond to a logically uniform system of thought. Respected Reverend Fathers, resource persons, teachers, and all the participants, greetings of the day to you all. I welcome you all to the valedictory program of Science Academies 5-day international online workshop titled Supernova and Neutrinos, organized by the Department of Physics, sponsored by Indian Academy of Sciences, Bengaluru, Indian National Science Academy, Delhi, National Academy of Sciences, Allahabad, in association with St. Philomena's College, Mysore. I now request Mr. Felin Amal, coordinator of this program, to welcome us.
Reverend Fathers, distinguished dignitaries, speakers, and participants. It is a wonderful moment to extend my warm welcome to you. We have with us Reverend Monsignor Leslie Morris, Episcopal Vicar for Education and Health Ministries, Diocese of Mysore, who always guides and motivates us in all our endeavors. On behalf of the organizers, I extend my warm welcome to you, Father. Reverend Father John Paul, Campus Administrator, St. Philomena's College Autonomous, Mysore, is here with us. On behalf of the organizers, I welcome you, Father. I extend my warm welcome to Professor Arthur Pinto, Director, PG Studies and Research Center, St. Philomena's College, who amidst his busy schedule is here with us. I welcome you, sir. I take the privilege to extend my warm welcome to our eminent speakers, Professor M.V.N. Murthy, Professor Vivek Datta, Professor Amol Dike, and Professor Kate Skolberg to this valedictory function. Welcome to you.
Thank you very much.
We have with us Professor D. Revanasithaya, Head PG Department of Physics, who has been our strength in organizing this lecture workshop. Welcome to you, sir. I also extend my warm welcome to Professor Shobna Thomas, Head UG Department of Physics, to this event. Welcome to you, ma'am. Finally, I welcome all the participants to this valedictory function. Thank you.
Thank you, sir. Three of the participants of this 5-day online workshop have come forward to express their opinions regarding the program. I now request the participants who will be providing their feedback to turn on their camera and unmute their mic as I call your name. First, I would ask Mr. Sridhar Prabhu to provide us his feedback.
Good evening, everyone. I'm Sridhar. I'm doing my master's in physics from University of Mysore. First of all, I'd like to thank PG Department of Physics for allowing me to participate in this lecture workshop. I feel very lucky and privileged to be a part of this workshop. The best part for me about this workshop was that it was highly professional. All the eminent speakers were to the point. Not for a single moment I felt that I'm totally lost and it is not for me. Since it's available in YouTube, I'll definitely refer it back. And the pace of the lectures were perfect. All the explanations were crystal clear. Uh, I also felt very proud and inspired that we have such great physicists in our country who are constantly engaged in latest research. I also thank Miss Kate for this wonderful concluding lecture. I also felt that the eminent speakers are experts in their respective field and with a lot of experience and have deep realization of the subject. All the participants are indeed very fortunate to hear from such great speakers. We are also fortunate that all the speakers were very kind and easy to approach, so that they would clear all our doubts. Just hearing them talking to each other between the lectures were interesting. Once again, I thank all the eminent speakers for all the lectures. It was just too good. Um, Credits to St. Philomena's College for organizing the workshop without any issues. The workshop was totally perfect all 5 days. It's a grand success like always. Once again, I'm grateful to PG Department of Physics for allowing me to attend, and I hope many more workshops will be conducted and we will be allowed to participate. Thank you.
Thank you, dear participant. I now request Mr. Shanmuga Priyan to provide his feedback.
It is a pleasure to give my feedback here. I'm working as a faculty in Lala College, Chennai, and I think this program was really a eye-opener. I think most of the students and faculties would have enjoyed. To be specific, I thank the Science Academies, Philomena's College, and the speakers extensively for their support and thing. We have traveled together during this 34th anniversary of first detection of supernova, observation through detection of neutrinos. I think we are happy to learn about neutrinos through talks of Professor Amol Dige, Professor Murthy, Professor Vivek Datta, and Professor Kate Skolberg. I think Kate Skarberg introduced us neutrinos as ghostly particles and emphasized the fact that they can't be seen, but their presence is always felt, and by means of interactions. We all have millions and billions of neutrinos, but we have handful of interactions. So she also emphasized on the large detectors and the time we need to run them to have much more physics. And Professor M.V.N. Murthy took us through the timeline of neutrinos, which was really amazing. And Professor Amol Dige, I think I'm hearing his talk for the second time. Earlier, I think I had his talk on mathematical methods in refresher course on mathematical methods in Mumbai. So I'm fortunate to hear his talk back again here. And he introduced us to the second most abundant particle in the universe, which are neutrinos, and said that there isn't direct mass measurement. That is, I think, a takeaway point for me. And he also highlighted about how neutrinos can be detected and took us through standard model and introduced us to the flavors of the neutrinos. And also he introduced about the neutrino detectors, and number of neutrino detections depends on three main factors: law of proportion, energy emitted, and interactions of neutrinos, which were I think amazing, which I learned new. And I think all the other talks were also amazing. Like Professor Datta's talk introduced us through nuclear properties and reactions of astronomical event, and I think it's lengthy. So I'd like to conclude saying that I thoroughly enjoyed. Although we the participants were invisible just like neutrinos, and we were asked to open up our mics and cameras to speak, and we were having limited we were expressing our presence by means of chats and listening to questions and talks actively. I hope a lot of students and faculties would gain more insights, and still there is a lot of area for research, and I think students who have taken part also will step in through this uh, get motivated and step to research in neutrinos. I hope so. I thank one and all for the opportunities back again. Thank you, professors, and thanks, Academies. Thank you all.
Thank you, dear participant. I now request Mr. Amoga Varsha M to provide his feedback.
Good evening to each and everyone. First of all, I would like to thank St. Philomena's College for organizing this wonderful workshop. It was a good 5 day journey that we had. Means most of the topics for new for me. Like I think most of us who are in the undergraduate level and the postgraduate level might not have heard and gone through all this. Means the topics, so it was very fascinating, and I would like to thank the Science Academies for organizing this workshop. All the lectures were very good for me. I felt each one had their own perspective, and the way of approach were totally different. The lecture by M.V.N. Murthy, sir, which emphasized the historical journey of neutrinos and supernovas, were very good, and all the lectures were very good, and also Professor Amol Dhike's introduction was very nice, and it was kind of in the level of UG and PG students, so that we can also understand the topic well. And Professor Vivek Datta's non-specialist view of astrophysics was, I felt it very good. So that when we share with our dear friends, so that they can, who couldn't attend this workshop, they can also go through all this thing, and they can also have a perspective of what's happening in the subject, means what's there in the subject, what's happening in this field. And at last, I would like to thank Professor Kate, who explained her research and the recent developments that are going in the field, and for her time, because I understand we have different time zones, and thanks to her for spending her time with us. And the YouTube streaming, which was made available, it is very helpful. And please, and I would urge the college to organize more and more workshops. Hopefully, we'll be able to come next time when the situation gets normal. So once again, I would like to thank each and everyone who made this event possible. Thank you so much. Thank you.
Thank you, dear participant. I now request Mr. Akhil EJ to provide his feedback.
Good evening, everyone. I'm Agize, currently pursuing MSc Physics in Central College, Mysore. It is my pleasure to give feedback on behalf of other participants who attended all 5 days of this workshop titled Supernova and Neutrinos. It was very informative and helped me to enhance my knowledge. Even though I'm pursuing my post-graduation, I had little knowledge about elementary particles, standard model, supernova, and other different aspects of stellar dynamics. This 5 day workshop helped me to understand this concept much more in detail. I thank Professor N.V.N. Murthy, Professor Kate Goldberg, Professor Vivek Datta, and Professor Noel D.K. for enlightening us with their knowledge. And on behalf of other participants, I thank Department of Physics, St. Philomena's College, Mysuru, for conducting this lecture workshop. Thank you.
Thank you, dear participants, for your valuable feedback. Those who have missed the video lectures, the videos are available on the YouTube for future use. I now request the convener of this program, Professor M.V.N. Murthy, to present the validity address.
Thank you very much. So this is, I'm going to speak only for a few minutes. And I'm extremely happy, and I was told that there were at least some 50 to 60 participants on the Zoom and more than 100 participants on the streaming platform. I think that's a very good number, and it shows the enthusiasm of the participants. And most of them were present on all 5 days, and it's very nice. So this topic of supernova 1987A is very close to me because I joined the Institute of Mathematical Sciences in later half of 1986. And in 23rd February 1987, the supernova exploded. I had a colleague, Professor N.D. Haridas, who knew about the astrophysical aspects of supernova. And immediately after we got the telegram from Astronomical Union that optical observation has been made, immediately he told me that there should be neutrinos coming and let us start working on it. And the next telegram from Astronomical Union also clarified that neutrinos have been observed, and they gave us those 10 to 20 events depending on which detector you are looking at that time. And that was completely summarized by my colleague, and we started working on for the next 20 days or so. I don't think we slept very much and worked on the supernova. And of course, Amol Digge and his work was not yet there to complicate things. So we could, in fact, using those observed events, we could arrive at some information, especially about what the binding energy of the neutron star, which came out of this supernova, should be. And in fact, we got a good order of magnitude estimate of the binding energy, which was about 10 to the power 53 arcs. And not only that, we used the time difference, the time spread of these neutrinos to obtain a limit on the neutrino mass, which for that time, it was a very good limit. So within a couple of weeks or so, we had our paper ready with Professor Haridas leading this effort, myself, Professor Joshipura, and Professor Indumati. And it was exciting. The supernova observation at that time was really exciting. And in fact, I think both Kate Scholberg and Amol Digge must have been in school at that time. Whereas I had just started my career as assistant professor in the Institute of Mathematical Sciences. So therefore, this whole topic of neutrinos and supernova is very special for me. And I'm extremely happy that St. Philomena's College and Professor Revant Siddhaya in particular requested me to have this workshop and agreed to have this topic for the workshop. So after that was the very first observation of neutrinos in 1987. Until then, supernova, all the historical supernovae were observed through optical telescopes. Now, for the first time, we have something like a neutrino telescope, which can see a supernova even when you cannot observe it optically. So, for example, if there is a supernova, as you learned in the last 5 days, which explodes in our own galaxy, you may not be able to observe it optically because it will be hidden by the matter distribution in our own galaxy. So therefore, neutrino observation is a new eye which has opened to the cosmos, and using that we can understand a lot of things about the universe, about the stars, and what is happening within the stars. And of course, in order to understand, you need a lot of things, and you need to know nuclear astrophysics, and the topics in nuclear astrophysics were covered by Professor Vivek Datar. And then the properties of the neutrinos, which we glean from other sources of neutrinos, not necessarily supernova, and those topics were covered by me. And how the neutrinos carry this cosmic message from deep inside stars was covered by Professor Amol Dige. And what are the observations and how we are going to use these telescopes, which are upcoming as well as the existing, to understand more about the stars, their explosion, their birth and death, as well as about the properties of neutrinos. And that was told to us from an experimentalist point of view, who is actually involved in these experiments, by Professor Kate Scholberg. All the talks were splendid, and I was so excited that I felt like a student all over again. And I'm sure many of you participants would have felt the same way. So I would like to thank all the speakers, Professor Vivek Datar, Professor Amol Dige, and Professor Kate Scholberg, for accepting this invitation to speak in the last 5 days, and telling the participants, in fact, enormous amount of information and conveying the understanding. And I also thank the college, the organizers, Fenella Amal and Professor Revana Siddhaya, and the college management and the principal for organizing this program so well and allowing so many participants to attend this workshop. And I should, of course, thank the 3 academies for their consistent support in organizing these workshops in colleges, in very small places, as well as in urban areas. So thanks to academies. And finally, thanks to you, all the participants, all the students and teachers who attended this, who asked so many questions, so many interesting questions. Thank you very much. You can continue to ask these questions. I'm sure you will find the email addresses of the speakers, and probably there are other experts. So if you have questions, you can always send it to them, and I'm sure they will answer your questions as the time permits. So thank you very much, and personal thanks to all the people in the college. Thank you.
Thank you, sir. It was a privilege to have you with us. I now request Reverend Monsignor Leslie Moraz, Episcopal Vicar for Education and Health, Diocese of Mysore, to deliver his presidential address.
Professor M.U.N. Murthy, the chief organizer of this wonderful program for the last 5 days, all the dignitaries on the days here, the resource persons and the participants. Honestly, I was very excited. A couple of days before the program started, Professor Evan Siddhaya and Professor Robna Thomas came and told me we are having this program. I knew something about supernova, I knew something about black holes and other things. When they said neutrinos, I was a little wondering. I knew about nuclein, I knew about neutrons, but neutrinos was a new thing for me. Immediately I started searching the Google search and trying to find out something. And I did collect quite a lot of information which was given in the inaugural, the first address itself. I was very excited to know about this new thing which constitute more than half the matter in the universe. And though probably whatever we know is something limited, and there's a lot of things to be covered still and learned about, I'm sure it is something which is very exciting. When I think about what is happening here, this field of astrophysics, trying to delve into the realm of astrophysics and try to find out what is it that our universe is composed about, and the whole aspect about particle physics, where they try to go deeper and deeper into the atom and the electron and the proton and the neutron and neutrinos and other things and all that. I think as human beings who are living at this particular age, at this particular era, have a lot of responsibility during the science age to probably go deeper and deeper and try to understand and see what has been the origin, what are things, the forces at work, the energy at work, and various matter that is there in the cosmos. On the one hand, when this excites us as not only scientists but even people like me, I think there's another thing also which reminds us, after all this flying in the air about trying to understand so many things about various new things, we have to come back down to earth. We are human beings and we need to live our day-to-day lives. And I think there is a big message for us when we go through lecture series like this, something which reminds us about our own entity. Very often, from sociological point of view, religious point of view, or political or economic, whatever it is, we try to put man as the crown of creation, as the master of the universe, as man who can do anything. I think an exposure of this type to the cosmos brings us back to what we are, who we are. Just a tiny, puny, nothing in this whole universe. I think that should give us the necessary humility to acknowledge the forces that are at work and ultimately draw our attention to the Creator who reminds us, yes, you live your life, you try to live it as best as you can, but remember that you are not the master. You're only just one aspect in this vast cosmos. I think that's a good thing for us. And I'm sure all the undergraduate, postgraduate students have enjoyed this. I try to follow most of the lectures, though a lot of mathematical things just go off my head. I could not understand them. But there are a lot of general information which I could gather, and I think it has given me a little more keener interest in trying to understand more about astrophysics and particle physics or whatever it is. I congratulate and thank the three academies which were actively involved to commemorate the memory of the anniversary of the supernova, which was observed on 23rd February 1987, and trying to make it available to the common public, to the students, and also St. Philomena's College, the PG and the PG people, and everyone involved in organizing this. And I think this type of lecture series should be organized more and more to help us to understand our cosmos better, to go deeper into science, to follow what is happening, the latest research. I never knew about the observatories for neutrinos. I have a lot more information today than what I knew before. So I congratulate everyone, thank all the people, and Murthy and his team and all the resource persons and everyone. And I only request that these type of things can be organized more and more. So make sophisticated science and scientific aspects accessible to common man. Once again, thank you all. Wish you all the best. Thank you.
Thank you, Reverend Monsignor, for your words. Link for the feedback will be posted in the comment section. On providing the feedback, you'll be receiving the e-certificate later. And the link will be open only for 15 minutes. Coming to the end of today's program, I request Ms. Namita SN, Organizing Secretary of this program, to propose the vote of thanks.
Greetings of the day to the respected dignitaries and to our dear participants. I feel honored for having given this opportunity to labor the vote of thanks for this 5-day Science Academies International Online Lecture Workshop on Supernova and Neutrinos. First of all, I spread my most sincere thanks to the Almighty for bringing us together for this purpose. I express my deep sense of gratitude to Reverend Monsignor Electron, Professor Vikat, MBES, who has always been a guiding light and source of motivation. Thank you, Chapel. I'm very grateful towards the college management for the constant support and encouragement in making this event a successful one. I express my sincere gratitude to Reverend Father Dr. Prakash Panas, Director Manager, St. Philomena's Institutions, Mysore, in his absence for his great support and motivation. I also thank Reverend Father Maria Savior, Vice Rector, in his absence for his kind support. I extend my warm thanks to Father John Paul, Campus Administrator, St. Philomena's College, for his unwavering support. Thank you. I'd like to place my hearty thanks to Dr. Ruchand Kumari, Principal, St. Philomena's College, Mysore, in her absence for her relentless support. I thank Professor Arthur Pinto, Director, PG Studies and Research Center, St. Philomena's College, Mysore, for her steady guidance and encouragement in all our endeavors. Thank you, sir. I must mention deep sense of appreciation to Professor M.V. Murthy, convener of the program, for his interest and enthusiasm in organizing the event. Also, as a resource person, he has brilliantly covered concepts of neutrinos, standard model, atmospheric neutrino problem. Thank you, sir. On behalf of the management and organizing committee, I would like to express my sincere gratitude and appreciation to our resource persons, Professor Amol Didi, Professor Vivek Kakkar, and Professor K. Stolberg, for their interesting and informative talk during the online lecture workshop. Further, I would like to thank the organizing committee of this event for their sincere efforts and hard work in planning and organizing this event. I must mention that we have been fortunate enough to be supported by a team of well-motivated and dedicated colleagues. I would like to extend my thanks to Professor D. Revanasitaya and Professor Shobana Thomas for their enormous support and guidance. I would also like to thank Science Academies for their generosity and support in conducting this 5-day international online lecture workshop. At this juncture, I express my deep sense of gratitude to Dr. Venugopal Gowda and Mr. Raviraj from Department of Template Journalism and Mass Communication, who has helped us to perfectly broadcast the entire event. I also would like to thank our students, Ms. Pooja, Master of Ceremony, and Mr. Akhil Krishnan, Mr. Akhil EJ, Mr. Kumar Kuttappa, Mr. Ibn Shaju, Mr. Arun Sani, Mr. Nikhil Stani, Mr. Jai Krishnan, and Mr. Alvin George for their assistance throughout the program. I express my thanks to our dear participants, without whom this program would not have been a success. Finally, I thank each and everyone who has been a part of this event for their participation and willingness to complete the tasks beyond their comfort zone. Thank you, Vanessa.
Thank you, madam. Thank you all once again. Have a pleasant day.
Thank you very much.
Thank you.
Thank you. Bye. Have a great evening.
Bye. Good evening.
Thank you, Professor Kate Scholberg. Thank you very much. Wonderful lectures, actually. Yeah.
My honor and pleasure. Very happy to do it.
We would like to have you again sometime.
Very good to see you all, at least as much as possible.
Okay, thank you.
Thank you. Good day to all of you.
Good day, sir. Sir, some lectures should be conducted for the school students, those who are interested in astronomy, astrophysics. some workshops should be conducted, especially in, you can 9th, 10th, 11th, 12th, that level. Because many children are very much interested.
Yeah.
I'm a school teacher. I'm from Pune.
Which school are you in?
I'm in Vidya Valley School, Pune.
Where is it?
Pune, sir, Pune.
Pune. Oh, I'm sure Vivek Datta would be able to.
Yes,
Once
sir.
the
Yes,
pandemic
sir.
is over,
Yes.
you can call him and he is close by.
Yes, sir. Yes.
And Amol Digge is also very close by.
Yes, both of them actually. Because many of my school actually they promote a lot of space education.
Yeah.
So many of our children they are going for that space. Even we went. I myself am a teacher liaison for space education. So if they are actually very much interested, our children. So some of the workshop, because this actually, if you see this workshop, when I attended, I thought, okay, I don't know what I'm going to understand. But I think if they listen properly, but children, they may need more guidance. Like I may not be able to help them understanding all these things. So some of the professors like you people are so senior. So
Sure. Please do contact,
yes, sir.
Professor Datar or anyone in, even in Pune, you have Ayuka.
Yes, sir. Yes, sir. Of course.
And I'm sure people in Ayuka can help you come and talk to children.
Yes, I'm going actually with our children regularly visit that they have lectures Saturday, second Saturday lectures are there.
Can I interject? I mean, there are these, I think, Science Day programs in the NCRA.
Yes, sir. Yes, sir.
So they have a very, I think, wide spectrum, and I think students attend that.
Yes, yes.
Maybe that would be. Have your school children attended those?
Yes, sir. Yes, sir. Every
Okay,
year.
very good, very good.
Yeah. Earlier 2 days program, now it is 1 day program.
Yeah, that's because probably the
Hello.
pandemic. Yeah.
If you want to communicate anything regarding, please write mail to us. We will communicate to respected professors. Thank you. Thank you.
Thank you. Thank you very much.
Thank you.
Thank you, sir.